In today's workshop, CARB staff will present to you the proposed methods of the 2025 Natural and Working Lands Carbon Inventory Update. We will walk you through the proposed methods that build upon the previous iterations of the Natural and Working Lands Carbon Inventory, and we want to solicit feedback on these methods with which the inventory will be updated. Next slide. Pursuant to AB 1279, CARB is responsible for identifying and tracking the state's pathway to achieving carbon neutrality by 2045. In support of this broader mission, CARB develops inventories of GHG emissions originating from both human industrial activities as well as annual to decadal changes in statewide ecosystem carbon stocks. The nature-based strategies section is responsible for assessing the total carbon inventory of all of California's natural and working lands. On the right-hand side, you see a diagram representing the 6 main categories of natural and working lands as defined by the International Panel on Climate Change, or IPCC. Furthermore, SB 901 directs CARB to publish a report on greenhouse gas emissions of wildfire, prescribed fire, and forest management activity. This report is a deep dive into the carbon impacts of forest management and wildfires. And for anyone interested, we also will have a public listening session on February 21st to talk about how we might track and account for land management activities with our sister agencies, especially in regards to 1757. You can go to our website to register or follow the instructions in the public notice that went out this morning. Next slide, please. CARB is tasked with tracking California's progress to meet its targets of achieving carbon neutrality by 2045. On this slide, you can see a simple equation that describes how we are thinking about carbon neutrality. Carbon neutrality is achieved when the balance of the state's AB 32 sources, that is to say, those from fossil fuels, landfills, and dairies, plus or minus natural and working lands carbon stock changes, minus any other sequestration methods equal or is below zero. Natural and working lands has a plus or minus sign here because these lands can either be sources or sinks of carbon. To quantify the contribution of lands towards carbon neutrality, CARB must assess the effect that climate, wildfire, droughts, pathogens, management, and anything else that impacts plants and soils have on these systems. Next slide. The Natural and Working Lands Carbon Inventory is the state's official carbon inventory and serves the critical role of quantifying the contribution of natural and working lands towards carbon neutrality. The Natural and Working Lands Carbon Inventory accounts for all organic carbon stored in living and dead biomass, near-surface soils, and harvested wood products within the state's legal boundaries. We want to emphasize that CARB is aiming to capture all plant and soil carbon within California's borders, regardless of ownership or if projects have occurred there. California's Natural and Working Lands Carbon Inventory is a tool that tracks the carbon stocks in all of the state's ecosystems and how they change over time. The inventory's purpose is to help California track progress towards achieving its various climate goals. The inventory does so by measuring progress towards our carbon targets and assisting with planning efforts. Next slide. CARB began working on its Natural and Working Lands inventory in 2006 with the first iteration of this inventory published in 2013, and the first Natural and Working Lands inventory report published in 2018 in response to SB 859. The Natural and Working Lands Carbon Inventory was developed and is maintained to quantify the contribution of natural and working lands towards the state's climate goals. It helps track progress against the -4% stock change target for natural and working lands set forth in the 2022 scoping plan, which rules that future losses should not exceed more than 4% compared to 2014 values. On the left-hand side, you see the breakout of carbon stocks by natural and working lands categories for 2014, where forests contain 85% of California's carbon stocks, while the other 15% are split across biomass and soils in the other land use category. On the right-hand side, you see how carbon stock change over time. In this graph, decreasing lines mean a loss of carbon from the ecosystems. This inventory estimates an overall loss of carbon stocks for forest and soil, while other categories like orchard and urban biomass show an increase over the same time, albeit on a smaller scale. Overall, the 2018 Natural and Working Lands Inventory estimated a loss of carbon in California's ecosystems from 2001 to 2014. Next slide, please. Since the last natural and working lands inventory was published in 2018, CARB has many new needs for the inventory, which necessitate new methods. For example, whereas the previous inventory did account for land cover change, there is now a more pressing need to quantify impacts of land management activities. The inventory will also be used as the foundation for tracking and assessing progress towards the nature-based solution targets as specified by AB 1757. We have also found that county air districts and other local planning agencies are more frequently needing to assess carbon stock change within their respective boundaries. CARB is interested in making the statewide inventory applicable and usable at these regional scales. Finally, there's a lot of new science and data available to utilize that wasn't available for the 2018 inventory. Ideally, CARB would like to take advantage of all relevant science that is available to inform the carbon inventory. Next slide. CARB is currently updating its methodology for estimating carbon stocks and carbon stock change for the 2025 Natural and Working Lands Carbon Inventory, and my colleagues will walk you through the details during today's presentation. Proposed changes to the estimation methodology of key components of the inventory include using open source model and observational input data sets, incorporating enhanced spatial data sets on the state of California's land cover, strengthening how disturbance events such as drought, wildfire, and land management activities change carbon stock estimates, developing a unified framework for estimating soil organic carbon across all land types, and updating estimates for harvested wood products using the most current empirical input data for the harvested wood products carbon model. Next slide, please. This slide shows a diagram of different tiers for inventory methods that are defined by the IPCC. Please go back. Thank you. As defined by the IPCC, the complexity of the tiers increases from tier 1 to tier 3 with increasing accuracy from left to right. Tier 1 uses global emission factors for a land use category and a standard global formula as defined by the IPCC. Tier 2 uses country-specific emission factors along with country-specific activity data by using a standard formula. Lastly, Tier 3 is defined as using a custom process model alongside country-specific activity data. CARB strives to use the higher tiers for its enhancements to the natural and working lands inventory. Next slide, please. As CARB worked to design new methods for the inventory update, guiding principles were developed that were used to assess the effectiveness of the proposed methods. It is not sufficient to dive into a large, complex problem like quantifying all carbon in California's landscapes without first understanding the problem and what you're working towards. These guiding principles are: for spatial scale, the inventory will be optimized to statewide scales with wall-to-wall coverage with sufficient accuracy at regional and county scales. For temporal scale, the inventory will go as far back in time as possible, at least to the early 2000s, and the inventory shall be as up-to-date as possible. Spatial resolution will be fine enough to ensure the resolution of ecosystem boundaries, allowing analysis on different stratifications across the inventory, for example, by ownership, management action type, land type, ecoregion, etc. Temporal resolution, the inventory will be reported every 3 to 5 years with annual values. Thematic resolution, the inventory will resolve as many carbon pools and fluxes as possible, but at least above ground carbon stocks and generally following IPCC guidelines. For sensitivity, the inventory must be sufficiently sensitive to quantify changes as a result of management and other major drivers of change. Priority here is to resolve the general magnitude and direction of change through time. And lastly, practical criteria. The inventory shall be based on open and transparent and repeatable methods that use free and open source based data. Next slide, please. In 2025, CARB will prepare the next SB 901 report on statewide emissions of annual greenhouse gas emissions associated with wildfires and prescribed burning activities, as well as changes in ecosystem carbon stocks associated with other non-fire enforcement activities. This assessment of the greenhouse gas emissions and carbon impacts of wildfire and forest management activities supports a better understanding of the effects of current forest management practices and disturbances and helps prioritize efforts to leverage natural and working lands for addressing climate change. This SB 901 reporting activity is conducted by CARB alongside the 2025 Natural and Working Lands Carbon Inventory update, but requires additional modeling work to estimate fire emissions as opposed to carbon stock change, which is calculated for the rest of the inventory. Next slide, please. Here's our draft timeline. This slide shows the timeline for CARB's 2025 Natural and Working Lands Carbon Inventory update and the reporting activity for SB 901. We're here at the public workshop in early February 2025. The inventory publication itself is planned for late summer of 2025. After the inventory publication, a public workshop on the inventory update results will be held in fall 2025. The SB 901 report will be published by December 31st, 2025, and CARB will then hold a public workshop and SB 901 results in early 2026. Next slide, please. This brings me to today's agenda. CARB staff have organized the presentations according to the standard IPCC land use category and the additional topics of harvested wood products and soils. You can see today's schedule. We'll start with soils, go on to agriculture and grasslands. Then there will be a short break, followed by forest and shrublands. In the afternoon, we will spend with the talks on harvested wood products, other lands, developed lands, and wetlands. Each topic consists of a 10 to 15-minute presentation, followed by a 15 to 20-minute period for comments. Each presentation is designed to be heard independently from the rest of the meeting, so as to facilitate the ability of people to pop in and out as needed. That means, just to warn you, that if you listen to the entire meeting, you'll hear some repeat refreshers on carbon neutrality and soil carbon mapping. Next slide, please. For this meeting, you should use Zoom in full screen mode for the best experience. If you have questions during the meeting, you can ask verbal questions by raising your hand or submit written questions by using the Q&A feature. After the meeting, you can provide general feedback via our website, the link to which is given here. For follow-up questions, you can also email us at nbs@arb.ca.gov, and the deadline for feedback is the end of this month, February 28th, 2025. With this, I want to again welcome you to the public workshop on CARB's 2025 Natural Working Lands Carbon Inventory Methods, and I will hand over the mic for the next presentation on soil carbon to Drs. Chelsea Carey and Tara Seeley. Chelsea?
So much, Matthias. Good morning, everyone. My name's Chelsea Carey. I'm a science and policy specialist at the Air Resources Board, and I'm a soil ecologist and biogeochemist by training. And this morning, I have the pleasure of walking us through proposed updates for the soil portion of the 2025 Natural and Working Lands Carbon Inventory. Next slide. So CARB's Natural and Working Lands Carbon Inventory, it focuses on soil organic carbon. And this is carbon that's stored in organic matter that originates from organisms like plants and animals and microbes. And organic carbon in the soil, it serves as quite a large reservoir. Globally, it stores about 1,500 gigatons of carbon to 1 meter depth. And to put that in context, it's more than is found in the atmosphere and plants combined. Carbon dynamically flows into and out of this soil reservoir via photosynthesis and soil respiration primarily. And the balance of these processes is affected by key moderators and drivers like soil type, vegetation, climate, disturbance, land management. And while much of this carbon turns over on decadal timescales, some of the organic carbon in soil remains stored for centuries to millennia. Next slide. The Intergovernmental Panel on Climate Change, or IPCC, it suggests breaking soils into two categories for inventory purposes: organic soils and mineral soils. Organic soils, they contain high amounts of organic matter, storing more than 12% organic carbon by weight, and they're developed under poorly drained conditions that can limit decomposition. In California, organic soils are primarily found in the Delta ecoregion, and that can be seen in the left-hand map there. And the majority of those soils have been drained for land use purposes at this point. Organic soils are also found, though, in coastal wetlands outside of the Delta ecoregion throughout the state. Mineral soils, by contrast, have lower amounts of organic matter, and they usually occur under moderate to well-drained conditions. And although I will say that they also underlie many of California's inland wetlands as well. And mineral soils cover the majority of California, which you can see in the map on the right. There are physical and chemical differences between these systems that require unique methodological considerations, which is why the IPCC guidance, it suggests adjusting them each individually. Next slide. CARB's Natural and Working Lands Inventory, it does consider both of these soil types, and it in fact documents soil organic carbon across all land types across the state. Estimates from the prior inventory can be seen on the right-hand side, and it indicates that 51% of the carbon in California's natural and working lands resides in the top 30 centimeters of soil. And I think this highlights the significance of this reservoir that we're looking at. Next slide. Prior soil carbon inventory estimates from 2018 were produced using a combination of methods. So this includes IPCC Tier 1 methods using global stock change factors for drained organic soils in the Delta, and that's shown on the left-hand side here. And this method assumed that all soils were losing carbon over time. On the right-hand side, Tier 3 methods were used for croplands remaining croplands, and these methods incorporated the denitrification decomposition, or DNDC, process-based model. And then all other lands used Tier 2 methods that relied on regionalized stock change factors, as well as standardized equations to determine changes in carbon stocks with land use over time. Next slide. So the prior inventory, it serves as a great starting point for us in this update. And with this update, we're proposing to build upon it by generating a unified framework that envelops all land types as well as soil types into a common Tier 3 method. The framework that we're proposing, it's really designed to take advantage of published and harmonized data sets as well as different modeling approaches in order to produce accurate maps of soil carbon stocks that incorporate the impacts of land management actions. And the hope and expectation here is that these updates we're making are going to reduce uncertainty of the soil inventory estimates, and that the framework will serve as a foundation for which we can incorporate future data and model improvements as they become available over time. Next slide. So I'm going to spend the next few slides unpacking this unified framework a bit more. And described at its highest level, we're proposing an approach that fuses empirical measurements with process-based modeling and machine learning to map soil carbon over the inventory period. And the first step in this process is to generate a time series data set by combining empirical measurements with outputs from process-based modeling at specific locations across California. Now, process-based models, they're mechanistic in nature. They're often used for simulating soil and ecosystem processes at project or field scales. And examples of some that we might be familiar with are DACENT, denitrification decomposition, or DNDC model, ROSC, as well as some others that are listed here on this slide. And these kinds of models excel at capturing temporal variability and at simulating systems in novel conditions. So using them to generate soil organic carbon estimates over the inventory period at point locations, it's going to help to bridge spatial and temporal gaps in a training data set and then ensure a robust foundation for the next step in our framework, which is to scale point estimates statewide using machine learning. Next slide. I've illustrated this first step of the unified framework graphically here for those who are more visually inclined. So on the left-hand side, there's this a cartoon diagram of a process-based model and as well as a time series of soil organic carbon values produced by it for a given location. And this time series is illustrated by that stacked cylinder where each layer is a carbon value for a different year, ranging from 2001 to close to as present as possible, here listed as 2023. So in those cases where process-based models aren't available in this framework or appropriate, we can use empirical measurements directly to contribute to the soil carbon training data set as well. And calibration of the process-based models, it's going to occur at representative sites across the state where detailed information on carbon and management and other factors are available. And then those calibrated models can be run on additional locations across known environmental and management gradients to help address gaps in the training data set. And what this is going to do is hopefully result in robust spatial and temporal coverage, which is illustrated by the cartoon map of California here. Next slide. So the choice of the process-based model that's used is going to depend on the land type being evaluated. ROS-C is being proposed for forests, grasslands, croplands, and developed lands. The cohort wetland equilibrium model coupled with the peatland ecosystem photosynthesis, respiration, and methane transport model, or SWIM peppermint, is being proposed for wetlands. And then other lands, shrublands, and drained organic soil land types in the Delta are going to be relying on empirical measurements if and as they're available. And individual land type presentations throughout today are going to have an opportunity to expand upon these process-based models or other empirical approaches more during their designated time slots. Next slide. The second step in this process is to scale the time series data wall to wall across California using machine learning methods such as random forests or boosted trees. And these methods are a form of empirical modeling that's widely used in digital soil mapping. And I do just want to take a second to describe what digital soil mapping is, because it's a formal term and you'll see it being used going forward as we talk about the unified framework. So this is a kind of mapping. It's a modernized process for creating high resolution maps of soil properties at landscape scales. And the idea behind it is that point-based estimates are used to identify and build relationships with covariates. And then these relationships can be used to interpolate carbon across the landscape. Machine learning is really well suited for this kind of landscape scale application, and it excels at capturing spatial variability with relatively low computational demand. Next slide. So I've gone ahead and incorporated this second step into the original graphic that was used to illustrate step one. And here we can see that the soil carbon training data developed in that first step will be combined with environmental covariates and anthropogenic covariates into the machine learning model. And once the machine learning model is developed, it can be applied to predict the spatial distribution of soil carbon across time for all of California's lands in this digital soil mapping approach. Next slide. So for this scaling step, the covariate layers, they must provide complete statewide coverage. So the covariates that we plan to ingest into the machine learning model include soil forming factors that are known to influence carbon, including those related to climate and vegetation, topography, and parent material. We're also going to include anthropogenic factors that may influence soil carbon over time, things like forest management, fire, cover cropping, grazing, and other land type specific layers as they're available. And again, individual land types will have an opportunity to expand upon these management and disturbance layers more during their designated time slots today. Next slide. So before we end this portion of the presentation, I wanted to take a moment and summarize the proposed updates for the soil inventory for 2025. We're introducing a unified framework for consideration that aims to comprehensively assess soil organic carbon across all land types in California. This framework, it integrates two well-founded approaches, process-based modeling and machine learning, with empirical-based measurements. And by combining these methods, we believe we can leverage the strengths of each to enhance accuracy and sensitivity of the inventory to important drivers of change. A key feature of this framework is its ability to facilitate Tier 3 assessments across all land types in a way that can quantify and display uncertainty. And finally, the framework, it's designed to be a solid foundation that we can expand upon as new data and improved models become available over time. Next slide. So I'll close there and open it up for discussion. If you have a question or a comment, you can raise your hand and you'll be called on, or use the Q&A function. You can also provide feedback after this session, as Matthias already mentioned, in written form using the instructions on the slide.
Okay, we have a question from Jonathan Sanderman. Would you like to speak, Jonathan? And also, I'd like to say that we want to keep the questions between just 1 and 2 minutes so we get everybody the maximum opportunity to speak and interact with the Nature-Based Strategies panel. So go ahead, Jonathan. Do you have a question or comment?
Sure. Can you hear me?
Yes, we can.
Okay, great. Yeah, sorry, you don't see my face. You just see my symbol. So Chelsea, And Matthias, thanks for the introduction and presentation. This is I like this approach, but I am very curious on how you're thinking about propagating uncertainty. So we know running point models at a point have enormous uncertainty on the order of 200 to 300%. And then you're going to be feeding that into a digital soil mapping framework, which will need to incorporate all that point level uncertainty and then include spatial autocorrelation in the outputs. So I'm just kind of curious if you've thought through this and kind of what the resulting output would look like, given that your training data is going to have a huge amount of uncertainty at any one point.
Yeah, thanks for that question, Jonathan. Well, yeah, I can speak to sort of our approach in general to assessing uncertainty here, and hopefully it gets at your question. I think uncertainty in the updated soil inventory, it's going to depend on data availability, model assumptions, and things like spatial variability. And I think it's going to be difficult to say at this stage, what level of uncertainty there's going to be, but there's a few approaches we can take to help evaluate and then communicate that uncertainty. And so for the process-based models, we can analyze variability in model inputs and parameters and structure using sensitivity analyses and Monte Carlo simulations to propagate uncertainties and key inputs, and then validate our outputs against independent soil data sets to assess confidence in our predictions. And then for the machine learning models, we can use performance metrics like R-squared and RMSE to evaluate model accuracy and using cross-validation against independent data sets to help ensure that they're robust. And then I think another key piece of this is communicating uncertainty and how we'll actually communicate what those uncertainty levels are. And so we can think about things like using confidence intervals or uncertainty ranges, providing uncertainty layers in our map visualizations, and potentially providing other qualitative descriptions of uncertainty. And so I think your point is well heard, Jonathan, and I think that that's something is going to be really important for us to be transparent about in our report.
Great, thank you very much. We have another question or comment from G. Ludwig. Would you like to tell us what you would like to say, or in terms of your question or comment?
Yeah, I have two questions or comments. One is just at a layperson's level, can you give a little bit of a sense of how this Roth-C model compares and contrasts with DNDC and or DACENT? That's question one. And then the other question is, how will you account for things like whole orchard recycling, where at the end of an orchard's lifespan, your trees are ground up and put into the soil? It's a major organic matter input that's a slow, that's there for quite a while. So just trying to understand how that will be incorporated in this thinking. Thank you.
Thanks for those questions. The Roth-C is a simplified process-based model, and it incorporates organic matter inputs of different sort of qualities and retention times within the soil or decomposition rates. And it is a widely used process-based model. We'll talk more about it in the grasslands and agriculture section, but it does differ from something like DNDC or DACENT in a number of ways. So DNDC, it's more comprehensive in that it includes coupled carbon nitrogen cycling, and it can simulate greenhouse gas fluxes. DACENT is coupled plant soil dynamic model. It integrates carbon and nitrogen and greenhouse gas fluxes, and it links plant growth explicitly. Roth-C is more simplified. It focuses on organic carbon dynamics, and sort of modeling the decomposition and carbon storage processes focused on that specifically, and not having these more sort of coupled dynamics in it. The way that, so there's inputs into Roth-C that account for organic matter quantity and quality. And so something like whole orchard recycling would, or any management practice that we're looking to simulate, will really be working, will really sort of be incorporated through modifications to those input parameters, the organic quality or organic matter quality and organic matter quantity. And then there's some other sort of ancillary parameters that can be modified, like temperature, precipitation, evapotranspiration. And so at sort of the highest level, those are the levers we can move in order to incorporate the effects of these different management practices, like those that would come with whole orchard recycling.
Thank you. I think we have another question or comment from a Kathleen Kilpatrick. Let me just give you, do you have a question or comment, Kathleen?
I do. Thank you. I'm not, this is a new area of subject matter to me. So forgive me if my question is ill-informed, but I'm just curious in those covariates, how and where you quantify the chemicals applied to soils. I'm thinking of like surplus nitrogen fertilizers, fumigants, and broad uses of herbicides, how those things factor in to the model as the impact they have on that 30 centimeters of soil, and also the whole carbon or nitrogen oxide thing, and that impact on greenhouse gases.
Yeah, so when we think about the capturing management effects through this unified framework, there's really two major components. It's one, how are we going to capture it in our point-based estimates through the time series empirical measurements and or our process-based models. And then also, how are we going to capture them in the scaling step for digital soil mapping? And so how they're captured is going to depend on the process-based model that's being used. And like I mentioned, there's various ones that are used, various approaches by land type, right? So one of the more common ones that we're proposing to adopt is ROFC, that's being used by 4 different land types. And in that one, things like fertilization, potentially other, management factors that you mentioned, it's on our team to think about how we expect those effects to translate into the system, and how we can modify the parameters of those models to reflect those effects. Now, it is a simplified model, so there's not going to be a lever for everything, but what it does, it has been tested across many different contexts and been shown to be generally robust and relatively accurate. And so really it's using calibration at sites to make sure that the model outputs we're getting under different scenarios are representative and as accurate as can be, and then going from there. For the digital soil mapping, in order to include spatial layers of any of these factors like nitrogen deposition or nitrogen inputs, we need those wall-to-wall, those kind of spatial layers across the state. And so really our hope is to be able to incorporate ones that we feel like are going to influence carbon, right? Because not everything is maybe going to have a really big lever, but the ones that we think are influence, thinking about how over time we can get access to sort of wall-to-wall spatial information on the application of these practices, so we can incorporate them as a layer in the digital soil mapping itself.
Great, thank you for that very thoughtful response, Chelsea. At this point, I don't see any people raising their hands, so I think what we'll do is we'll entertain some. Oh, there's someone, Priya Arya. Let me just give you some chance. All right, Priya, do you have any questions or comments that you would like to make?
Yes, thank you so much for your presentation. Can you hear me okay?
Yes.
Yes, we can.
So I don't know how much, since this is a relatively new methodology, has there been any thought as to how using this model can allow you to attribute improvements in soil carbon sequestration attributed to any specific measures a locality or maybe the state government will take in terms of driving sequestration, maybe through afforestation or reforestation? Are there ways that this model helps attribute changes that you see to direct actions or decisions made, or is that not, are we not there yet?
Yeah, I think that that's so the moving forward, the natural and working land carbon inventory, the methods are going to, we're hoping to enhance the sensitivity of the inventory to land management activities. So yes, that's a goal here, is to be able to incorporate land management activities into this and be able to understand their effects on carbon over time. And the Natural and Working Lands Carbon Inventory, it's a tool that's going to act as a basis from which we can assess the impacts of 1757 nature-based solution climate targets as well. So that this is a key component of the inventory, is to be able to just understand the effects of land management interventions that are happening across the state on carbon over time.
Thank you, Chelsea. We have another question from a Sarah Aird. Sarah, would you like to ask a question or make a comment?
Yes, thank you so much. I actually have two quick questions. One is, are these, I may have missed, just not heard this, but are these models accounting strictly for carbon, or is it also including other greenhouse gas emissions from natural and working lands related activities, is my first question. My second question is the model accounting for more holistically types of practices such as regenerative organic farming that encompasses a multitude of practices that are often different and integrated versus more conventional farming methods, and how is that being accounted for?
Sure. Okay, so for your first question on if we are looking at other greenhouse gases or just carbon, the inventory by and large focuses on carbon stocks right now. The one exception is in wetlands, and Kyle, my colleague, Dr. Kyle Lunenberg, will talk about that a little bit later today. The AB 32 greenhouse gas inventory captures emissions for other sectors across California, but for natural and working lands right now, this inventory focuses on carbon stocks. We are working on a contract to, for some of our land types, generate models that will also estimate greenhouse gas emissions for the inventory going forward, because it is an ultimate goal of us, of our work, to be able to get to estimating and quantifying emissions. But right now, our inventory, we're focusing on carbon stocks and stock change. For holistic versus conventional management practices, ultimately, we want to capture all of it and be able to assess the impacts of all of it. It's going to be a process to get there, but that is our intention. And things like to be able to capture all of the investments that are happening statewide.
Great, thank you, Chelsea. And we have another person asking a question, Amaya Kosla, and I apologize if I'm.
Yeah, hi. I had a question, and it looks like that my question, which was typed into the chat, will be answered, I guess, during this session. So thanks anyway.
Thank you.
No problem. So I think at this point, we still have some time. I don't see any hands being raised. Let's go to questions that were posted in the Q&A. Oh, no, we have another one stepping up to the microphone. Alicia Mulkey. Alicia, do you have a question or comment you'd like to make?
Yeah, can you hear me as well?
Yes, we can.
Yeah, just to keep drilling in on the kind of cropland management, I'm still not clear, and I'm also new to this conversation, so I may just be ill-informed, but what data set are y'all recommending for the cropland kind of farmer management record? So the cover cropping, the rotational grazing, the nutrient inputs, is that farmer-led surveys? Is that other data you hold? Are there points where y'all have prescriptive sampling points over time? I just not clear on that answer.
Yeah, Alicia, if I may, I don't know if you're able to stick around for the agriculture and grassland section, but we're going to talk a lot more about that in that section. So I might leave some of the answers until then. And if you want to follow up, I'm happy to do so as well.
Okay, this time I think there are no hands being raised. Unless someone wants to raise their hand and speak, that's perfectly fine. If not, I'd like to take a question from the Q&A from Robert Parkhurst. What data sources are you using for the various data elements, soil type, climate, slope, etc.?
Mm-hmm. Yeah, so for the digital soil mapping, I expect that's what you're asking. Yeah, so yeah, we have some sources identified that we're considering for those environmental covariates. So for climate, CalAdapt, looking at, things like mean annual precipitation, temperature, climactic water deficit, conceivably. For vegetation, things like land type, cover, MPP, we can use things like land fire or MODIS and Landsat. For topography, using something like the USGS digital elevation model. If, as we incorporate layers related to parent material or things like pH and texture, we can look to things, layers like the gridded NATSCO, which is a combination, a combined sort of layer from the USDA. And then getting into management and disturbance layers, we'll talk more about these in the different land types. But there's various ones that we're considering for the management and disturbance covariates as well. So for example, forest management, we can look to land fire or CNA treatment tracker. For fire, things like CAL FIRE's historical wildland fire and perimeter maps, etc.
Great, thank you, Chelsea. Another person asked, this is Craig Thomas, will there be monitoring of soil carbon levels and changes over time for organic agriculture, regenerative ag, and more traditional agricultural practices?
Yes, great question. I think I've hopefully answered it a little bit already, but and just to clarify that by and large, our staff are not out there monitoring soil carbon. We rely on partnerships and publicly available data sets to acquire and ingest empirical measurements into this approach. And so if you all have ones that you manage or know of that you think would be a good fit, we welcome we welcome that. And then for the different management types, organic, agriculture, conventional, regenerative. Again, it's the intention of the inventory to capture all management that's happening on California's landscapes, and it's going to be a process to, for us to get there. But yes, hopefully, all of the management factors that we believe will affect carbon, ultimately, we want to be able to understand and capture and assess those.
Great, and then Jenny Blaker asks, can you explain what boosted trees are?
Yeah, so they are a type of machine learning model, so machine learning it's this data-driven approach that uses algorithms and learn patterns from data to make predictions. And two common kinds are random forests and then boosted regression and boosted trees. The boosted regression and classification trees, they build these classification or decision trees sequentially. And so they're learning by correcting errors of the previous one that's been made for higher accuracy. And so the whole idea here is that they want to be able to accurately predict something like soil carbon based on these other covariates that it's provided. And a boosted regression classification tree is just one way to do that sort of sequentially to increase accuracy of that prediction in the process.
Thank you very much, Chelsea. I think it's 9:45, so we need to move on to the next section, which is on agriculture and grasslands. And this will be convened by Dr. Tara Seeley.
Thanks, Jim. Good morning, everyone. Thanks for joining us today. I'm Dr. Tara Seeley and my colleague, Dr. Chelsea Carey, who you were just hearing from. Both of us will be presenting today on CARB's proposed methodology for quantifying carbon in agricultural lands as part of the Natural and Working Lands Carbon Inventory. Next slide. This presentation focuses on agricultural lands, which are represented by the Intergovernmental Panel on Climate Change, or IPCC, in two distinct categories: croplands, which are visualized on the left, and grasslands on the right. Next slide. Croplands encompass roughly 9.5 million acres, as shown in the map in gold. And as you can see in these images, croplands take a variety of shapes and are one of the most actively managed landscapes. Cropland management is influenced by economics, physical changes like a shifting climate, and regulations like the Sustainable Groundwater Management Act and the implementation of nature-based strategies. Agriculturally, croplands support several industries, for example, the $11 billion almond industry. Next slide. Grasslands include 9.7 million acres, which is shown here in the map in green. Grasslands are dominated by herbaceous plants with less than 10% tree or shrub cover, and as you can see in these images, provide several important functions. Agriculturally, grasslands can be irrigated and managed for grazing, providing support for the $4.8 billion cattle industry. Grasslands can also be natural landscapes, providing wildlife habitat and critical water resources. Currently, grasslands are affected by increasing pressures from invasive species and drought. Next slide. So as you all know, California has an ambitious goal to reach carbon neutrality by 2045. Next slide. And the Natural and Working Lands Carbon Inventory addresses the contribution of this middle term, the natural and working lands, towards our goal of carbon neutrality. In croplands and grasslands, we track carbon stocks, specifically in the form of plant biomass and in soil organic carbon. So today we're presenting a few key methodological enhancements that build on the last iteration of the inventory, which occurred in 2018. And we're looking forward to your feedback and suggestions. Next slide. The carbon stored in croplands and grasslands is dynamic and affected by a multitude of drivers. Climate, vegetation, and topography are all known drivers, but management can also potentially influence carbon stocks. This table shows the nature-based solutions, or NBS, climate strategies and their corresponding 2045 targets. Conservation is an NBS for both croplands and grasslands, as well as healthy soils practices, which encompass a suite of strategies intended to improve soil and landscape resilience. Croplands also have a percentage-based organic agriculture target, and grasslands have a target for promoting beneficial fire, reducing fuels, and planting trees to restore oak woodland. One goal we have in our carbon inventory is to design methodology which will be sensitive to these various to the various impacts that these management strategies may have on carbon stocks. Next slide. In croplands and grasslands, there are three categories of biomass carbon: annual croplands, perennial croplands, and grasslands. Next slide. First, annual croplands are herbaceous crops, like the tomatoes shown here, that stay on the landscape for less than a year, or in some cases, a few years. For annual crops, we assume biomass is ephemeral because it is grown and subsequently removed from the landscape, as shown in this mechanical harvest of a cereal crop. Because annual cropland is not a persistent carbon stock, it is not considered in our natural and working lands inventory. That being said, residues from these crops are a consideration that we can incorporate into soil carbon modeling, which will be discussed later on. Next slide. Second, perennial croplands in California specifically are woody orchards growing nuts and fruits like the almond trees shown here. In contrast to annuals, woody perennial crops are a more durable form of carbon that is persistent from year to year. The carbon we quantify is stored in the roots, trunks, and branches of the trees. Next slide. CARB defined allometric equations for key orchard species in previous inventories. Allometric equations help translate orchard trees by their age and identity to carbon content. The orchard species these equations are defined for are listed here: almonds, walnuts, pistachios, oranges, and vineyards. Together, they compose 88% of the orchards in California by area, or the yellow portion of the pie chart. Next slide. Carbon allometry was first developed on an individual tree basis based on measurements of tree height and diameter and combined with USDA allometric formulas. So in this figure, we can see carbon stored by the tree on the y-axis and how it increases with tree age, which is shown on the x-axis. In the case of the almonds shown here, the oldest tree samples stored over 1,000 kilograms of carbon. Next slide. These allometric relationships do vary by tree species. So as you can see, the relationships between tree age and tree carbon are somewhat different for walnuts, oranges, and pistachios compared to almonds. Next slide. Tree carbon must be scaled to the field level using orchard tree density or tree spacing. So multiplying tree carbon by tree density gives us a value of carbon per area. We can use these carbon density values to estimate carbon based on the acreage of a specific orchard type and its respective age. Next slide. So this brings me to our first key new feature, building upon the 2018 inventory. The 2018 inventory used data from the National Agricultural Statistics Service, or NASS, which spatially summarizes the acreage of each orchard type every 5 years. Now we have access to a remote sensing derived map of orchard type and orchard age. This data set is produced by the Department of Water Resources and their contractor Land IQ. In the sample pictured here, you can see orchard type and year planted are delineated in yellow boundaries. This map has greater detail and accuracy compared to NASS summer statistics, and it includes orchard age, which sets it apart from other maps, other products like the cropland data layer. The proposed methodology is to apply the allometric equations to this map of orchard type and orchard age in order to derive carbon estimates. Next slide. The second key new feature is related to the light green slice in the pie chart, which represents the 12% of California's orchard area composed by tree species that have not been defined allometrically. Examples of some of these undefined species are listed here: peaches, plums, avocados, olives, and cherries. Next slide. A new inventory feature is to produce estimates of allometry for these tree species based on a few key data sources. First, we will rely on published wood density measurements. And second, we will use measurements of tree size and form to scale and estimate allometric equations. Two such data sources include tree height and tree spacing. Next slide. The final biomass carbon pool is found in grasslands. So again, grasslands are dominated primarily by herbaceous grasses with less than 10% tree or shrub cover. The quantification of biomass carbon in grasslands is focused primarily on forage production, which is the total biomass produced. So let's walk through the methodology workflow, which was adopted from work by researchers at UC Davis. We combine measurements of NDVI, or Normalized Difference Vegetation Index, from two satellite products named Landsat and MODIS. Blending these two data sets leverages the advantages of both. Landsat provides high spatial resolution at 30 meters, while MODIS provides high temporal resolution at daily intervals. These satellite measurements can tell us the total amount of energy absorbed by grassland plants. Towards the end of the workflow, biomass clippings will be used to calibrate estimates of plant productivity. The final output will be a spatial map of annual forage production. So this approach is responsible for the key new features in grassland methodology, which are increased spatial resolution and accuracy, and this will yield spatially explicit biomass carbon estimates in grasslands. I will now hand the presentation over to Dr. Chelsea Carey, who will be discussing the soil organic carbon component of croplands and grasslands.
Great, thanks so much, Tara. Okay, so we're going to move on to discuss soils for croplands and grasslands now. And as I described in the prior presentation, for this inventory update, we're proposing to use a unified framework that maps soil carbon across all land types, which includes annual croplands, orchards, and grasslands. And so this framework is going to be open source and aims to improve the specificity and accuracy of soil carbon estimates across all land types in California, in part by incorporating management and disturbance effects. And so The first step in this framework, as a reminder, is on the left-hand side, and it's to generate a time series training data set by combining field measurements with output from process-based models that are tailored to specific land types. At points across California, soil carbon measurements are going to be estimated in this first step for 2001 to as close to present as possible, so 2023, something like that. And this is graphically represented by that stacked cylinder there. These models are going to serve to bridge temporal and spatial gaps and ensure robust foundation for machine learning. And then as we move right on this diagram, outputs from these models are going to be aggregated into this training data set and then combined with environmental and anthropogenic covariates for digital soil mapping, which uses machine learning to estimate soil carbon distribution across California over time. Next slide. For croplands and grasslands in this framework, we're proposing to use the Ross-C model to generate these time series estimates of soil carbon at point locations. And I talked a little bit about it last session, but Ross-C, it's a simplified biogeochemical model. It was developed from Rothamsted Research Site in the UK in the 1990s. And in the middle is a simplified diagram of the model itself. And I'll go ahead and walk us through it. So at the top, you can see the model. It incorporates inputs of organic matter. So these are things like plants, manure, compost, and that feeds into the organic matter pools that have different characteristics and retention times within the soil. And carbon is either stabilized in the soil or released as CO2 through decomposition in this model. And then what remains is the organic carbon pool, which is what we're interested in for our purposes. Ross-C, it also has the ability to incorporate climate data that using temperature and precipitation and potential evapotranspiration to model how environmental conditions influence decomposition rates and carbon storage as well. And we did evaluate multiple models that are commonly used for estimating soil carbon in these systems, and Ross-C stood out for a number of reasons. So unlike models we all might be familiar with, and we talked a little bit about in Q&A last session, are Baycent and DNZC, Ross-C's completely open source, which was a requirement that we were seeking for our model selection. It also has a simplified structure, which is nice for scaling up and adoption. And then importantly, despite its simplicity, it performs comparatively well at predicting soil carbon across diverse contexts. And in fact, it's been widely used to predict soil carbon across many land types globally, and it does well within grasslands and cropland systems specifically. And Ross-C, it has precedence in national greenhouse gas inventory, so being used in this manner. It's used by both Australia and Switzerland in their national inventories, and it can represent management regimes that we care about and disturbances that we want to represent, which was another requirement for this update. Next slide. I'm going to spend a couple slides talking about how we'll incorporate management and disturbance information into Ross-C, as well as a digital soil mapping exercise for scaling point estimates statewide. And so Ross-C model parameters, they can be adjusted to reflect the impact of various management and disturbance regimes that occur across California's croplands and grasslands. And for this inventory, we're going to begin by using site-specific data to simulate cover cropping and livestock grazing and fire, which are common across these land types. Now, Ross-C is able to simulate more management approaches and disturbances, and we're interested in leveraging it to do so as we're able to identify and secure data from appropriate calibration sites. Next slide. So once we have accurate point location estimates of soil carbon dynamics under common management and disturbance conditions for these land types, then we have wall-to-wall management and disturbance layers that need to be combined with other environmental covariates into machine learning model that will be used to scale them statewide. And so focusing on those same three management and disturbance regimes that I highlighted in the slide prior, we propose to incorporate cover cropping into the scaling step by using Land IQ crop map developed by the Department of Water Resources. And a snapshot of that map can be seen at the top right of this slide. And then livestock densities can be incorporated into this scaling step by combining a gridded livestock of the world map with county ag statistics and as necessary, CARB's dairy and livestock database. And the gridded livestock map is shown here in the middle. It was developed by combining national and subnational livestock statistics with predictor variables like vegetation and climate and topography, human demographics, and it created a statistical model for livestock densities globally. It's widely used including in the Global Livestock Environmental Assessment Model, or GLEAM, which is a well-adopted model used by national greenhouse gas inventories to estimate emissions from the livestock sector. And then finally, we propose to begin by incorporating fire using CAL FIRE's historical wildland fire perimeter as a disturbance layer in this scaling step as well. In this layer, it's refreshed annually to provide up-to-date information on fire perimeters across both public and private lands in California. Next slide. So just to take us full circle, once we're done with these two steps of the unified framework, we'll have statewide maps of soil carbon over the inventory period. That's going to allow us to assess both spatial and temporal changes with land use management and disturbance. Next slide. In order to leverage the full capabilities of this approach, we need to have access to diverse calibration sites, as well as spatial information on management and disturbance across California grasslands and croplands, including some of those practices that are listed here, things like compost application, tillage, whole orchard recycling, range seeding, grazing systems, etc. And we're actively seeking out data to inform and evaluate our models from a range of sources, including from academics, private landowners, and nonprofits, to join survey data that we have access to as well from different government entities. And so this is an effort which is ongoing. Next slide. And we're going to continue to compile information related to carbon and management practices going forward. And we certainly welcome any input that the public has in that regard. Next slide. So I'll close this there again and open it up for discussion. If you have a question or comment, you can raise your hand and you'll be called on, or use the Q&A function. You can also provide feedback after this session in written form using instructions on the slide.
Great, thank you very much, Chelsea. And again, I'd like to remind people to try to keep their questions to 1 to 2 minutes, though I'd have to say most of the attendees speaking today have been very concise. So thank you very much. The first question we'd like to, or comment we'd like to entertain, is from Joel White. So Joel, do you have any questions or comments you'd like to ask?
I briefly just missed the total acreage of grasslands. I think cropland was 9.5 million.
Sure. Yeah, grassland total acreage is 9.7 million.
Thanks for that.
Sure.
Okay, we have another question or comment from a Robert Parkhurst. Robert, would you like to ask your question or make your comment?
Yes, thank you very much. Can you hear me?
Yes, we can.
Great, thank you so much. So I'm curious how, well, two parts of the question. One, why aren't you using the USDA methods approach? They've got a document that they just recently republished. I think it was in August of this year or April of this year, with the latest science on quantification. So that's part one of the question. And part two is, how do you think the method will compare to the methods document, since you aren't using it? Thank you.
Yeah. Thanks for that question, Robert. The USD methods that I believe you're speaking to are largely focused on project level assessment, if I am thinking of the right methods document that was released. And so it has a different scope than what we're looking at, with us focusing primarily at the state scale. We do align ourselves with IPCC principles and recommendations, which aligns us with other inventories and inventory methods, including at the national scale for the US. And so we should be aligned in that way. And then for some of these other methodologies, the difference is often at the scope and scale that they're looking at, with many others being project level.
Great, thank you. And we have another question from G. Ludwig. G, would you like to ask your question or make your comment?
Yeah, one question I had was, so I work with almonds. In many of our fields, we have where the irrigation system is and you get moisture, and where you have dry areas. So I'm just trying to understand how these models, do they deal with, or do you just do it sort of on a area-wide basis, that you have two completely different soil ecosystems going on in many of these systems. That's question one. And the other one is just trying to understand more about what exactly you're looking for the kind of data, because we at the Almond Board fund research, so we have, well, the researchers have data on whole orchard recycling, compost, and so forth. So we're just trying to get a better understanding of what you're looking for there and to whom do we talk to about it.
Can you repeat your first question, please? Oh, maybe she was not. No, she
Yeah,
doesn't
sorry,
have
I
it
was
yet.
removing, I think yeah, I apologize. I just had to move on to the next speaker.
That's okay. Maybe Tara heard it and can respond to that one.
I can jump in on the first question. So just to paraphrase what I heard, it was there's a lot of heterogeneity, right, in almond orchards with respect to moisture, particularly. So areas where it's more wet, areas where it's more dry. It's very different. So how does this kind of factor in to our quantification approaches? And I think that's a really good point. And it's something we deal with our inventory methodology, right? Like these landscapes are very complex. Croplands are very complex. There's a lot of heterogeneity. What we're striving for is capturing carbon estimates on the county and statewide scale. So to the extent that there is heterogeneity, as long as we're capturing sort of the aggregate impact to carbon, that's our aim. That's what we're striving for. And so we feel the methodology that we've selected can handle those differences and ultimately help us get our goal to that county statewide quantification.
Thank you for that very thorough response, Tara. Our next question or comment comes from Kathleen Kilpatrick. Kathleen, would you like to make your comment or pose your question?
Yeah, I still am a little confused of how you link the stocks research with the emissions reduction research in agriculture, and I'm just what it looks like from how you've described what you've been looking at so far is that the large commodity products like the nuts and the citrus and the vineyards that they're on your map, but the smaller things are not so much on the map. And I'm just concerned, especially like since I know the Almond Board does their own research, what's going to be lost if you don't get information from the more diverse and smaller agricultural operations that are really what we need to combat climate change and to make our food system accessible to the people who live in the state of California. How does that get factored into your model? Do people have to know that this is happening and on their own initiative submit their data? I know that there are some growers in the Salinas Valley that are doing some innovative methods to collect data. So how do those different kinds of agriculture get factored into your model that seems to be focused on what I would call the commodity crops of California?
I'll start, and then if Tara wants to add anything, we're interested we care about accurately capturing carbon sort of on every square inch of California. So this includes all land types, all production systems within croplands. And we are doing a lot of work to do outreach to try to secure data sets and ensure we have representation across the diverse land types and contexts that underlie all of these important production systems within our state. And so certainly the intent is not to focus on large sort of commodity crops. We care about all of it. And I think that this is something that this inventory we are attempting to incorporate the sensitivity to different land management practices and to different cropping and sort of that are incorporated into different cropping systems. And we can always improve. So going, through time, we'll be looking to incorporate more and more information as it becomes available so that we can reach our ultimate goal, which is to quantify carbon across all lands, regardless of ownership, through time.
Thanks, Schulte. I also just want to add that to your point about our outreach efforts for data, we have been reaching out to academic partners, nonprofit partners, and we're still in a phase where we're seeking input and suggestions. And so we're still interested in data. And I also wanted to go back to a previous question about the types of data. Soil organic carbon measurements are really important, but then we also are seeking information on land management practices. So field sites where we can quantify which practices were implemented, like cover cropping, no-till, the area, the extent that was implemented in, all of that would be very valuable for us. So this is an ongoing effort. And again, part of the reason why we get a lot of value from these public workshops is because we're looking for suggestions and opportunities to potentially solicit more data and more suggestions. Thanks.
Thank you very much, Tara. Also, we have a question or comment from Margaret Reeves. Margaret, would you like to make your question or comment?
Yes, thank you very much. Margaret Reeves from Pesticide Action Network. First of all, thank you very much for the presentation. A lot of good information. I have to absorb it all. But following up a bit from Kathleen's comment and about data needs and acquisition, two things. One is in looking at more diverse management practices, I really encourage you all to look to those practices that are less common and be presenting them as a model for moving forward for transition for change, rather than focus on what's already there. And so some of the elements, as already mentioned a bit, but agroforestry systems, I do understand that you've got good data for many specific species, but where we talk about a mix, and you had the slide that showed how you're going to estimate analysis for different tree species, but I also think it's important to include other mixed woody systems like hedgerows and again agroforestry systems. So I'm just encouraging you to actually put a little extra weight on those systems that might not be as common currently, but have great potential and could provide very important information for learning and for helping us move forward. Thank you.
Thanks, Margaret. I really appreciate that. And I just want to remind you that when you have valuable feedback like that, we are taking comments at the website posted here, which will help us document all of these really helpful suggestions. So thanks so much.
Thank you very much, Tara. At this point, I'd also like to state that we are answering and responding to questions posted in the question and answer feature throughout the course of the workshop today. And like Tara says, if you, at the end of the workshop, you can still post comments to our public website. I'd like to entertain a question or comment from a Chance Cutrano. Chance, do you have a question or comment that you'd like to make?
Yeah, thank you so much. Chance Cutrano from the Resource Renewal Institute in Marin County. We're a nonprofit that does a lot of work with farmer producers and also work on natural lands as well. But I'm curious if there is, you've alluded to this a couple of times, just the outreach to academics and NGO partners with regard to data sets and trying to accumulate more information about practices that are being implemented. Is there a more formalized process for land managers or landowners that want to raise their hand for calibration sites or for that want to help expedite the process of gathering these sorts of information, or is it kind of just getting off the ground and you all are kind of doing outreach selectively to folks that you've been identifying? Just trying to figure out how to be most helpful in closing some of those information gaps, or helping to encourage land managers that may be interested but aren't aware of this, who would want to have a calibration site or something like that. So that would be helpful to know. Thank you.
Yeah, thanks for that question, Chance. I would encourage them to, whoever has, is interested in that, to reach out on our website through the submission portal or through our email that's listed here. And we are certainly looking and interested in folks who want to volunteer to share with us. We would welcome that. And so while we have focused our efforts on, those that we know about, we certainly recognize we don't know all of the data that's out there, and we would like to know more. And so I would encourage whoever that is that you're thinking of to submit via our website or follow up with at that email.
Great. I have a question or comment from an Anna Larson. Anna, would you like to state your question or comment?
Yes. Hi. Good morning. Thank you so much for your presentation. I'm Anna Larson with CalCAN, the California Climate and Agriculture Network. And I think some of these questions have been along similar lines around, hearing your thoughts on how you're thinking about the calibration sites. And I was wondering how you're thinking about the Healthy Soils program and the data information there, and how that could help.
Yeah, great question. Thanks for that, Anna. So for this inventory, we're not going to be incorporating CDFA's Healthy Soils incentive program carbon data. The data produced doesn't currently align with the specific requirements for CARB's natural and working lands carbon inventory analysis. And CDFA is in the process of developing more standardized methods and protocols for tracking the impacts of Healthy Soils program incentive projects. And so we'll look forward to sort of keeping an eye on that over time in partnership with CDFA. For the demonstration projects, that's something that we will be looking into more. The demonstration projects are more research focused, and we will be working with our partners at CDFA to explore incorporation of those data into the inventory.
Thank you, Chelsea. And at this point, I'd like to kind of remind everybody that we'll be having a public listening session in the future on the 21st of February regarding AB 1757, methods for tracking and assessing the effects of land management in California's landscapes. We will go into detail about how we track nature-based solutions and nature-based strategies regarding land management for California's natural and working lands. We have a question or comment from Adam Chambers. Adam, would you like to tell us what your question or comment is?
Hi there. Thanks a bunch. Great presentation. I appreciate what you're doing there in California. My question is regarding some of the semantics that have been used, and you've mentioned carbon calculations multiple times and trying to include different sources and sinks of carbon. I presume that what you really mean there are carbon stocks, so that you can look at carbon stock changes over time. I think some of our other questions have alluded to this, but really what you're going to do is, if I understand it correctly, you're going to want to analyze carbon stocks at T0 and carbon stocks at T1 and find the difference there in a methodology similar to the national inventory. Would you mind clarifying that piece? And then I've also heard you reference two different depths, a depth of up to 1 meter, and then I've heard you reference 30 centimeter depth, which is consistent again with the national inventory. I'd be curious which one of those approaches you're going to take, and if you're going for the deeper 30 to a meter, how much data you have on that kind of soil carbon dynamics down to a meter. Thank you very much.
Thanks for those questions, Adam. So to answer your first question, that's correct. So we're looking at change over time in carbon stocks in vegetation and in soils. And so we'll be looking, we're estimating carbon stocks at T1, T2, T3, sort of across the inventory period, starting with something like 2001, going to as close to present as possible. And then we'll be looking at the differences over time in those carbon stocks. So hopefully that clarifies that piece of it for you and for others. And then to your second question, thanks for raising that. Yes, we will be looking just at soils to 30 centimeters, which is aligned with IPCC recommendations.
Great. We have another question or comment from Sarah Aird. Sarah, would you like to tell us what your
Hi, this is actually not Sarah. I was using her link. My name's Jan Dietrich, and I was very blown away by the presentation at the EcoFarm conference by Dr. Jennifer Petridge at Lawrence Livermore Lab on the soil microbiology and especially these new insights about the viruses racing along the hyphae and the growing root tips of plants, and this depth of the description of what's going on in highly productive soils. I imagine you're networking with Lawrence Livermore, but I want to make sure you are, because that team is really discovering stuff. Thanks.
Thanks for that comment. Yes, we do know the staff and scientists, many of the staff and scientists from Lawrence Livermore, including JP or Jennifer Petridge, and their work. And the microbial community is absolutely critical to soil carbon cycling and storage, and is, are drivers of a lot of the change that we'll be capturing with our methods.
Thank you for that. At this point, I'd like to reiterate that we had scheduled a break around this time, but in the interest of kind of entertaining more questions and comments regarding soils, agriculture, and grasslands, we're going to continue until 10:30 when we start the next session.
Jim, I think you may have cut out there. Okay, you're back now.
Yeah, apologies. I'm kind of switching between different screens. Apologies to everyone here. We're going to forest and shrublands in the next session, but we're going to continue through what was originally planned to be the break and to entertain some more questions and comments. We don't have any more raised hands. So at this point, I'd like to kind of go to some of the questions written in the question and answers feature. One that was written a bit earlier on, but I think is appropriate to a number of different sessions, and it comes from John Blue. And he writes that you mentioned the use of publicly available data. Are any of these published by the federal government? There is some concern about the current administration continuing to publish a lot of ongoing work.
Thanks for that question. Yes, many of the data sets that we use are managed by the federal government. They produce some of the best statewide remote sensing data that's available to us, for instance, and which our methods currently rely on. And in addition, they maintain foundational field-based data sets that are critical for our work as well, and many people's work for that matter. That being said, no matter what happens with the federal government's, with the federal government and accessibility of these data sets, CARB is committed to producing the best inventory that science and data will allow.
Great. The next question that we have here is from Alicia Mulkey, which is what data sets are you utilizing for cropland management of cover crops, rotational grazing, tillage, etc.?
Yeah, thank you so much for that question. To answer your question, it really depends on the specific management approach. So we have a wide variety of different data sets that we track down for those various practices. So for example, with cover crops, some of that information about, the rotation of crops is actually going to be found in the Land IQ data set in their most recent iterations. So that's a tool that we're going to be using for that practice. And then other practices we might not have as spatially, explicit information about. And in some cases, we might have to rely on, other reports of how widespread these practices are. And in that case, if spatial data, is not available, we're going to have to infer the implementation of practices through other means. But this is, it's an ongoing effort, and our efforts, we sort of track down the best available data possible, and we also try to keep tabs on the data sets as they emerge.
Thank you, Tara. We have another question from an Anthony Collin, who asked, as larger numbers of private landowners contract to collect their own data, will there be any clear routes for those data to be used for the revision of these models and the inventory?
Yeah, that's a good question. I mean, for right now, the clearest route is for and sort of the route that we have established is for folks to be able to reach out to the email that's listed here. Going forward, it's possible we would come up with different processes to facilitate ingesting information as they come up. And if that was the case, we would communicate that with the public with the means that we have at our disposal.
Thank you, Chelsea. We have another comment or question, or sorry, a question from Priya Arya. Does California have to work around legal protections for farmers from disclosing data about what they produce and their activities? If so, what has worked in driving data collection?
Yeah, I can take a stab at that. So data privacy is something that we understand is a really important concern and consideration for sharing of information with us from private landowners. We have been working together to create a data intake form to understand users and contributors' preference for data sharing. We do at CARB also really value creating open source, open access workflows. And so to the extent possible, we want to be able to make the information and the pipelines that we produce be publicly available. That could include the data that we use, but again, we recognize privacy issues, and so to the extent that's possible by law, we will honor those requests.
Thank you, Chelsea. Reagan O'Leary asked, considering that the grasslands as we know them today are dominated by non-native Mediterranean grasses that don't sequester carbon as well as native perennials, is there going to be a push for restoration of native grasslands?
Thanks for that question. That is beyond the scope of the carbon inventory. The carbon inventory doesn't recommend any management actions itself, and I would maybe point you to some additional resources like the AB 1757 nature-based solutions targets that can give you more information on the state's work there.
Thank you, Chelsea. We have a couple clarifying questions from Sarah Aird. Am I correct that one of the main purposes of the inventory is to identify and then encourage practices that are more climate friendly? If that is correct, how are these models taking into account other practices of farming that don't directly deal with crop and soil management, but do impact carbon and other greenhouse gases, such as whether farms sell produce locally versus sell nationally, or farms that use or don't use petroleum products such as fertilizers and pesticides?
I can take this one. Thanks, Sarah, for that question. So the main purpose of the carbon inventory is to capture the contribution of croplands and natural and working lands more generally towards carbon neutrality. So our efforts are trying to integrate everything that has already happened on the landscape into a measurement of the carbon stock that exists. And I just want to highlight that because we strive to be sensitive to different land management activities, including those that are considered climate smart. And so while our methodology is intended to reflect the effects that those management practices have on carbon stocks, our goal is not to, identify or promote one practice over the other. The inventory is an objective scientific measurement of the carbon stock that exists on the landscape. So I just wanted to clarify that, but then also acknowledge that those practices are built into our methodology because we strive to be sensitive to the effect that they produce.
Thank you for that response, Tara. Margaret Reeves, I see you raising your hand, but unfortunately we have to keep on schedule and move to the session on forests and shrublands, which will be started off by Dr. Matthias Falk. Thank you, Matthias.
Thank you, Jim. Next slide, please. All right, hello again. My name is Dr. Matthias Falk. I'm the lead scientist for the Natural and Working Lands Inventory Program here at the Industrial Strategies Division at the California Resources Board. And today I'll be giving a short introduction on the efforts to update the methodology for the forest and shrubland inventories. Next slide, please. CARB's Natural and Working Lands Carbon Inventory assesses historical changes in ecosystem carbon for California's forests and shrublands, as well as the other land types that you've already heard and will hear later. SB 901 additionally directs CARB to publish a report on annual greenhouse gas emissions of wildfire, prescribed fire, and forest management activities every 5 years. In this context, it's important that a carbon stock refers to a static measurement of stored carbon, while greenhouse gas emissions represent an active release into the atmosphere. The Natural and Working Lands Carbon Inventory assesses carbon stocks and stock change over multi-year timescales. Additional steps are needed to quantify greenhouse gas emissions from fire and management activities. This is because even though carbon stocks may be lost from fires, we need to determine how much of that stock change goes into the atmosphere as CO2, as greenhouse gas emissions are only one pathway amongst others. This presentation includes sections detailing the upgraded methods for the natural and working lands inventories for forest and shrublands. Next slide, please. As you heard before, CARB is tasked with tracking California's progress to meet its targets of achieving carbon neutrality. And again, this slide shows a simple equation that describes how we are thinking about this carbon neutrality. Carbon neutrality is achieved when the balance of the state's AB 32 sources associated with fossil fuels, landfills, and dairies, plus or minus natural and working lands emissions, minus any other sequestration methods, equal or below zero. Natural and working lands here have a plus or minus signs because these lands can be either sources or sinks of carbon. To quantify the contribution of lands towards carbon neutrality, CARB must assess the effect that climate, wildfire, droughts, pathogens, management, and anything else that impacts plants and soil carbon through its natural and working lands inventory. Next slide, please. Okay, this slide will be slightly different than the rest of the presentations today in that we will have 3 speakers and will present in sequence. Following the presentations, we'll have the feedback period for all the presentations. Each presentation will take approximately 10 to 12 minutes each. And first, I'll give an overview of the upgrades to the Landfire C tool used for the previous 2 natural and working lands carbon inventories. Then Dr. Ryan Bart will present a section on a new forest inventory ensemble approach. And lastly, Dr. Karl Lanneberg will present a section on shrubland inventory upgrades. Next slide, please. Within natural and working lands of California, forests are the second largest vegetation category by area, comprising about 27% of the total area. Most of this forest area is concentrated along the north coast and the Sierra Nevada. Forests contain the most carbon out of any of the vegetation types, making them a critical component of the natural and working lands inventory. Forests are defined as locations with greater than 10% canopy cover here. Further, forests are susceptible to many drivers of change. These include disturbances such as wildfires, pathogens, and drought, type conversion to other land covers such as grasses or shrubs, management, and climate change. Next slide, please. In addition to the natural drivers of change, management changes established by AB 1757's nature-based solutions climate targets can also potentially influence carbon stocks in forest. These are acreage targets for the forest associated with the nature-based solution climate targets as required by AB 1757. Wildfire risk reduction natural-based solution targets include 1.5 million acres of beneficial fires per year by 2045, 1 million acres of other fuel reduction activities also by 2045. Forest natural-based solutions climate targets include afforestation of oak woodlands in areas where they were historically found to the tune of about 53,000 acres per year by 2045, conservation of old growth conifer, riparian, and oak woodland forest at about 55,000 acres per year by 2045, restoration following high severity fires, as well as restoring the health of degraded oak woodlands with about 320,000 acres per year by 2045. Finally, improving the functioning of management forest, including extending harvest rotation lengths, shifting in the intensity of harvest, and conserving wildlife habitat at about 165,000 acres per year by 2045. There are 2 percentage targets for forests that include a decrease in the rate of illegal forest conversion and degradation by 90% by 2045, and an increase in beneficial fire and fuel reduction activities that should lead to a reduction in the percentage of high severity fires, so that low to moderate severity fires collectively will make up 90% of all wildfires by 2045. Next slide, please. Landfire C is a carbon accounting tool based on landfire land cover and disturbance change data from landcover.gov and US Forest Service forest inventory analysis plot to data biomass densities. Landfire C was developed by Battles, Gonzalez, and Sa for CARB under 2 contracts in 2013 and 2016. The current implementation contains refinements of the above ground, rangeland, and other carbon estimates implemented in the 2nd contract. Next slide, please. The diagram on the right-hand side shows the general Landfire C workflow. As you can see, Landfire C uses the following inputs: vegetation type, Landfire EVT, canopy cover percentage, Landfire EVC, canopy height, Landfire EVH, and disturbance data from Landfire, which shows when and where different types of disturbances like fire and management occurred. To convert these metrics to carbon, a model was developed and calibrated to FIA data to create Landfire C outputs of carbon stocks by pool and carbon stock change for any inventory year analyzed. Next slide, please. Current challenges for this method include the Landfire updates its classification system regularly by splitting vegetation types, for example, requiring constant refreshes of the model that converts Landfire inputs into carbon stocks. Also, access to FIA plot data is limited, which limits our ability to update the carbon stock conversion functions and regional growth factors in Landfire Cs. Furthermore, remote sensing cannot see post-fire deadwood and will show no carbon on the landscape after fires often. This can lead to overestimating the immediate impact that wildfires have on carbon stocks. As a result of this current state of the science limitation, most all carbon maps have a hard time quantifying post-fire carbon stocks, and Landfire C is no exception here. That is to say, if a forest is subject to a catastrophic wildfire and all of those trees burn, they may not all combust, and much of the carbon will remain on the landscape. But remote sensing has a hard time seeing deadwood, including logs and snags. CARB acknowledges this challenge and is currently working on enhancing this aspect of our mapping efforts. Next slide, please. For the 2025 carbon inventory update, Landfire C is undergoing the following updates. Regular updates are being made to the model that converts Landfire inputs to carbon stocks via lookup tables. We're also working to enhance CARB's mapping effort of post-fire deadwood. This will include the incorporation of a new deadwood module into Landfire C for pixels, where fire transformed forest into other land use types. We will leverage CARB's in-house fire modeling expertise to better estimate combustion that occurs due to wildfire. This will allow us to incorporate better estimates of the post-fire carbon stocks on the landscape into Landfire C. Finally, we're working to produce annual estimates of carbon stocks. This will allow us to track deadwood and other carbon pools that remain on the landscape by taking into account decay rates and subsequent disturbances. Next slide, please. There are a number of other updates to the framework we use to run Landfire C that are being currently developed. First, we're migrating the Landfire C framework to a high-performance computing cluster. This requires us to convert the Landfire C framework to rely solely on open source tools, and this framework will use open source geospatial data formats. The forest carbon inventory will use previously presented unified soil carbon framework to estimate forest soil carbon. For forest, this approach will use a modified approach with Modus NPP inputs to drive the soil carbon model ROS-C. And with this, I will now hand over the presentation to my colleague, Dr. Ryan Bart. Ryan?
Thank you, Matthias. Hello, my name is Dr. Ryan Bart, and I'm a scientist here with the Nature-Based Strategy section at the California Air Resources Board. Today, I'll be describing, in addition to our work to help quantify and assess forest carbon as part of the natural and working lands carbon inventory. Next slide. California is in a fortunate position that since the 2018 inventory was produced, multiple groups have developed above-ground carbon products for California, providing unique approaches for estimating forest carbon across the state. The models, methodologies, and datasets underlying each of these approaches provide different strengths and weaknesses. CARB plans to leverage the expertise and knowledge underlying each of these products to enhance California's understanding of forest carbon stocks via an ensemble. This approach expands on the previous Landfire C approach by incorporating other carbon estimates that exist in California. A way to think about this approach is the Coupled Model Intercomparison Project, or CMIP, where multiple research groups around the world produce global climate model projections, and then the results are compared among the groups. CARB wants to do something similar by taking advantage of all the science and work performed here in California to help CARB's understanding of forest carbon dynamics. Next slide, please. Now, before we go any further, I'd like to clarify what an ensemble is. An ensemble is an approach that allows multiple data sets to be included in a carbon time series. In the left panel here, we can see an example of a single carbon product through time. This approach takes into account a single data source that estimates carbon for 3 different years. Alternatively, in the right panel, we can see an example that also uses the first data source, but also includes additional products, each of which is likely to provide slightly different insight. Ensembling is a technique that combines the results from multiple models to form one model estimate. This single model has the potential to illuminate insights that a single model may not be able to provide. For example, this exercise will provide a measure of uncertainty in our forest carbon predictions, as we will produce a range of carbon estimates. Next slide, please. This figure details the ensemble approach, which contains multiple parts, each of which I will speak about in more detail in subsequent slides. The first step is to obtain the different carbon products from the groups that produce them. These will generally be provided in the form of raster time series. The second step is to validate each product. Validation involves comparing each carbon product to a separate validation data set in order to evaluate how well each product is performing. And finally, we process the ensemble itself and generate outputs. Next slide. I'll now go into each of these methodological components in more detail, starting with the products themselves. Next slide. The ensemble approach will bring together multiple spatially explicit carbon products, developed both in-house at CARB and from external projects. CARB will be establishing criteria that the carbon products must satisfy to be considered for ensemble membership. All products that meet these criteria will be evaluated for inclusion, including products operating at global, national, state, regional, and local scales. Each carbon product will be required to estimate total above-ground live carbon, as this variable will allow comparability among all the data sets. In addition to a total above-ground live carbon, multiple secondary variables of interest to CARB, such as total below-ground carbon, total above-ground dead carbon, understory carbon, and litter carbon, will also be incorporated into the ensemble if these data sets are available. These secondary variables provide a more comprehensive picture of how carbon throughout our forested lands is distributed among the various forest carbon pools. These secondary variables will also contribute to non-inventory CARB needs, such as fire emission estimates. Next slide, please. I'll now discuss how we will approach model validation. Next slide. CARB will assess the quality of each carbon product using an independent validation data set of total above-ground live carbon that CARB is assembling. CARB is working to make this validation dataset as representative of California's diverse ecosystems as possible, and will likely include federal, state, and local inputs produced through field-based measurements. Based on the validation, contribution of the carbon products will be weighted within the final ensemble carbon estimate, such that the best products will contribute the most. For example, in the table on the right, If product number 2 performed best during validation, it would provide a larger contribution to the final ensemble result. Meanwhile, if another product, such as product number 1, does poorly in validation, the influence of that product on the ensemble will be minimized. This validation procedure will allow us to understand the products we are incorporating and generate the best ensemble estimate. For regions of the state where validation is inadequate to assess the quality of a carbon product, an alternative approach will be used that identifies high confidence pixels. High confidence pixels refer to pixels within a spatial data set, such as a raster, that exhibit a high level of reliability and accuracy in their values based on specific criteria. These high confidence pixels will be used to evaluate and weight each potential ensemble member. Next slide, please. I will now discuss the ensemble process itself. Next slide. The ensemble approach provides flexibility for estimating forest carbon. For each pixel throughout the state, a mean and variability metric can be generated, providing an estimate of which regions of California have better agreement than others. These pixel level estimates can be aggregated to regional and state levels, providing carbon inventory estimates at larger or smaller scales as needed. As mentioned previously, one of the major advantages of the forest carbon ensemble process is that it provides a carbon estimate based on all available science, methods, and data. The challenges associated with the ensemble approach are largely related to the statistical robustness of the carbon estimates due to the still limited number of carbon products available for the ensemble. With a relatively small number of ensemble members, examples of potential issues include biased data sets and an inconsistent number of ensemble data points available for inference during individual years. There may be further issues related to the temporal continuity of products if methodologies have changed over time. When possible, CARB will work with the groups that are generating each carbon product to identify potential issues and refine the methodologies as needed. That said, the generation of the validation data set, which will provide guidance on which products to weight more than others, should lessen these challenges. Next slide. Now to summarize. CARB plans to introduce an ensemble approach of forest carbon products to inform the forest carbon inventory. All products will be validated against an independent data set, allowing us to weight the products within the final ensemble estimate. This ensemble will bolster our work using Landfire-C. However, the exact extent to which the ensemble contributes to the inventory will be determined as this work develops, because this exercise's success is highly dependent on the data that CARB can acquire, the robustness and representativeness of the ensemble members, as well as the practical aspects of working with many diverse groups to collect and harmonize complex data sets at different scales and with different temporal and spatial resolutions. We expect that this work will produce invaluable insights into forest carbon within California. And with that, I'll say thank you. And we'll now transition to the shrubland inventory and my colleague, Kyle Lenenberg. Kyle?
Hello, everyone. My name is Dr. Kyle Lenenberg. I am a nature-based solution scientist with the nature-based strategy section here at CARB. Today, I'll introduce the proposed methodology updates for shrublands and chaparral. Next slide, please. So under IPCC guidance, shrublands and chaparral are nested within the forest land type. However, the methodologies used to calculate carbon stocks within these systems differ substantially from forested ecosystems. Within California, shrublands are currently the most prevalent vegetation category, covering approximately 31% of the state. These lands include any shrub-dominated area with greater than 10% canopy cover of shrubs and less than 10% canopy cover of trees. This includes a wide range of arid, coastal, inland, montane, and steppe ecosystems. These are extremely diverse sets of communities occurring across the entire state. The primary drivers of change in these systems include type conversion, management, and climate effects. In chaparral systems, excessively frequent wildfire can result in type conversion, where ecosystems such as annual grasslands replace stands. Wildfire can also be an agent of change in the other direction. Forested lands that burn in high severity are often at risk of type converting to shrublands, or at least having a delayed reestablishment period. Management has major effects, including fuels treatment, restoration, and other actions. And finally, climate, especially in areas with changing precipitation, wind, and temperature patterns, can directly affect carbon stocks or interact with other drivers, such as wildfire. Next slide, please. Alongside the National Working Lands Carbon Inventory, as Matthias mentioned, in April 2024, Governor Newsom announced specific nature-based solution climate targets. In shrubland and chaparral communities, these targets call for increasing action of 140 to 150,000 acres of climate action every year between now and 2045. These targets will affect conservation and restoration in a huge variety of shrubland ecosystems, such as the sage scrub, montane chaparral, and coastal shrubland communities in the depicted photos. In developing an updated methodology to the inventory, our methods must be able to track the implementation and carbon consequences of these targets. Next slide, please. As mentioned, the previous methodology, Landfire-C, associates empirical biomass data with predictive remote sensing data sets. Those are land fire's ecosystem type, canopy height, and canopy cover percentage products. As seen in the right figure, land fire products are connected to input reference data with compatible metadata, either explicitly or spatially explicit plot level data or allometric equations using canopy height to quantify biomass carbon stocks. Most of the empirical data within Landfire-C was derived from forest inventory analysis, or FIA, plot data. However, the FIA program does not sample a majority of shrubland and chaparral communities in California, requiring additional biomass densities as inputs for these ecosystems. These densities were sourced from literature-derived allometric equations by Gonzalez et al. In 2015. As with other empirically derived models, part of Landfire-C's strength is that we can continue to update these underlying data sets as new data becomes available. Since the last update, new data has been produced that can build upon the already implemented literature values. Part of the challenge in using literature values rather than plot level data is that allometric equations are usually published for an individual shrub species rather than for a 30 meter by 30 meter area, the resolution of land fire. Really, the ultimate enhancement to the system would be to track every single shrub individually in the state. As this is likely not feasible for this ecosystem, or at least not yet feasible, enhancing the resolution of canopy cover change would be beneficial. An enhanced resolution could also provide a connection to allometric equations that rely on predictors other than canopy height, such as canopy diameter. Next slide, please. In the displayed figure, you'll see the shrubland and chaparral ecosystems included in the 2018 National Working Lands Carbon Inventory and the associated biomass carbon density parameters as calculated by Gonzalez et al. In 2015. Within the plot, you'll see the average total carbon, which includes below ground, dead, litter, and above ground live carbon stocks in metric tons per hectare. These average values are modified by canopy height and canopy cover by Landfire-C to map densities across shrubland communities. To update the underlying data sets or data inputs to Landfire-C, we'll conduct a literature review of available biomass carbon density data that's been produced since 2015. Part of this update will be ensuring Landfire-C scales the literature-derived allometric equations to plot level estimates in the most accurate way possible. In this update, the resolution of ingested remote sensing data will be critical to correctly couple the literature-derived values with Landfire-C. Next slide, please. So this connection to high-resolution imagery will come from the second update to the previous methodology, a remote sensing analysis using NAPE imagery. NAPE, or the National Agricultural Imagery Program, is a remote sensing product put out by the U.S. Department of Agriculture. When compared to satellite products, NAPE imagery has a much higher spatial resolution and a lower collection frequency. This imagery is collected every 2 years in California, providing high-resolution imagery for tracking change at those temporal scales. Within the proposed methods, NAPE will be used to connect the literature-derived carbon density data with Landfire-C and track the effects of management and disturbance events, particularly those events that are not currently captured by the land fire disturbance products. Next slide, please. So here's an example of NAPE imagery and how it may be used to track canopy cover within shrublands and chaparral. In the left 3 photos, you'll see aerial NAPE imagery of 3 different shrubland sites across California with differing canopy cover percentages. In the right 3 images, you'll see the canopy cover percentage calculated as an NDVI threshold. An NDVI threshold uses spectral indices to quantify the percentage of vegetated pixels. In these right three images, white pixels denote areas that were detected as shrub versus ground. While NDVI performs well in these example images, part of this work will be finding the appropriate spectral index or segmentation scheme to accurately quantify canopy parameters and detect shrub density across the state. Further, additional work will be required to ensure that grasses are not being misidentified as shrubs. This will include an explicit verification of accuracy. This method is appropriate to explore in shrublands as opposed to forest because of the lack of understory that is not clearly visible under closed canopies. As you can see in the less dense canopies, that first row, we are clearly able to distinguish individual shrubs. In these cases, we can extract features such as the number of individuals and crown size diameter directly. We may not be able to collect this information for all systems, as seen in the more densely packed canopy coverages. In these systems, we will require additional information to determine the best connection to literature-derived allometric equations. Next slide, please. So here's an example of the second benefit from this NAEP analysis. On the left is aerial imagery from NAEP in 2010 of a semi-deciduous coastal sage-grouse community. On the right is the remotely sensed canopy cover again with white pixels denoting vegetation. Next slide. 4 years later, the site experienced a wildfire. We can see the same location on the left using NAEP imagery and the remaining canopy cover in the right image. Note that within shrubland and chaparral communities, fire frequently results in the total loss of above ground vegetation. Next slide. However, given an otherwise healthy ecosystem, shrubland communities can recover from wildfire fairly quickly. In 2016, in the same image, we see the start of recovery. Next slide. 2018, recovery continues. Next slide. And in 2022, canopy cover is approaching its previous extent. In this way, this NAEP analysis allows us to explicitly track the effects of wildfire and other management events that directly affect canopy cover. The benefit of this approach over canopy cover percentage provided by land fire is the ability to track small-scale impacts over the entire state that may not be captured within land fire's disturbance products, and better connect these impacts with literature-derived allometric equations. Next slide. The other half of the inventory effort, as already mentioned, is to quantify soil organic carbon in the upper 30 centimeters of the soil profile. As mentioned earlier in the soils methodology update presentation, all land types will use a unified soil approach, which integrates statewide data sets and ecosystem-specific drivers of change to quantify soil organic carbon. Displayed is a 10,000-foot overview of this unified effort, starting from the left. Literature time series values of soil organic carbon are integrated into a statewide database. Digital soil mapping is performed using environmental drivers, management, and disturbance maps that are specifically tied to primary drivers of change for each ecosystem, as seen in the central panel. Once the digital soil map is developed, it can be applied to predict the spatial distribution of soil organic carbon across time for all of California's shrublands, as well as quantify the uncertainty underlying our predictions, as seen in the right panel. Next slide, please. So here's an example of one of these ecosystem-specific drivers that's important for soil organic carbon in shrublands. Frequent wildfire in shrubland and chaparral communities can often result in type conversion to other ecosystems. The figure on the right displays the percent fire return interval departure with negative values and warmer colors depicting an increase in wildfire frequency when compared to historic baselines. We find that many of the shrubland and chaparral communities of Southern California, in particular, experience much more wildfire than is thought to have occurred previously. Although there is very limited data explicitly tracking the change in soil organic carbon due to frequent wildfire in shrublands, coupling data sets such as the land fire disturbance data with our statewide synthesis of available soil core data can capture cumulative impacts that taking yearly snapshots alone without knowledge of previous disturbances cannot capture. Next slide, please. So in summary, proposed updates to shrublands and chaparral methods within the Natural Working Lands Carbon Inventory will integrate new biomass and soil carbon data sets. Biomass carbon data sets will be integrated through the land fire seed tool, building upon the existing empirical relationships using new literature and time series values across a range of management regimes and disturbances. Remotely sensed canopy cover of these ecosystems over time will directly quantify the effects of management and disturbance and improve the relationship between remotely sensed data and literature-derived allometric equations. Finally, additional soil organic carbon data sets will be integrated with the Unified Soils Framework with specific covariates for shrubland and chaparral communities. Next slide, please. With that, we can open it up for questions and comments. As a reminder, here are the instructions on how to pose a question or submit a comment. Please try to keep questions or comments to 2 minutes. We'll give you a friendly reminder when you've reached the 2-minute mark, although that hasn't been really necessary yet.
Okay, I think the three presenters talked about quite a lot of material today. I'm not seeing anybody raising their hand at this point. Oh, we do have someone, Dennis Baldacci. I apologize if I'm not pronouncing your name properly. Do you have a question you'd like to ask or comment to make?
Hi, I'm Dennis Baldacci. I'm a professor at UC Berkeley, and I was really impressed that you guys are approaching with the ensemble approach towards the carbon modeling of the forest. I think it's really critical. I would even add to have a hierarchy of model approaches. And one of the realities is the difficulty of assessing all of these respiration terms, both autotrophic and heterotrophic. And I think as another suggestion is in the flex world, we find a really tight relationship between annual global primary productivity and ecosystem respiration. The slope's about 0.85, R squared is about 85% based on several thousand site years of data. And so I guess I would toss that into your mix as another way of comparing net ecosystem exchange of carbon dioxide between forest and the atmosphere, especially since you all can do a pretty good job of modeling GPP with remote sensing, either using traditional light use efficiency models, or I even encourage you to use the approach of my former student, Youngwil Ryu, who has this Breathing Earth science simulator that couples carbon water fluxes, because in California you have a lot of ecosystems that are limited with soil moisture, and you only get carbon fluxes right through photosynthesis when you mix the two. So I think those are my suggestions to add to your ensembles, and yeah, keep up the great work.
Thank you, Dennis, for those valuable insights. I really appreciate your insights and your long career in this field. We surely look forward to talking to you more about this in the future.
Yeah, I don't think we have any hands raised at the moment, but somebody asked an interesting question in the question and answer feature from Jenny Blaker. At the beginning, you mentioned carbon stored in emissions. What about carbon sequestration?
All right. Yeah, so just to talk about that, when we showed, I think everybody has seen the slide on carbon neutrality now a few times, right? So we have the plus minus there indicating for natural working lands, indicating that we can have stock change in both directions, right? And so and it's really important to highlight the fact that the inventory tracks carbon stocks and stock change over long terms, and any kind of like flux in and out of the system on shorter time scales, like is going to contribute to that stock change over long periods of time. But we really need to look at this on a 4 to 5 year scale to really kind of assess the change of carbon stock on the landscape, and that's what we're tracking with the inventory. So like the inventory will show whether the systems are losing carbon over these long terms out of the stocks or gaining carbon, and like a lot of different flows and of carbon in and out of the systems can happen due to management, disturbance, all sorts of things. And we're here to kind of assess the net effect of all of these things and then keep track of it so that the state of California can make informed decisions in the future.
Thank you for that, Matthias. Jenny Blaker had some follow-up questions. Before we get to that, I'd like to address an earlier question was raised at the very beginning of the workshop from Karen Pitts. Doesn't forest thinning increase carbon?
So as far as forest thinning, the current inventory, the carbon inventory that we're producing is kind of agnostic to the types of treatments that are going on. When treatments or disturbances happen on the landscape, the carbon inventory will pick up those differences in carbon on the landscape, but it won't necessarily, it in and of itself doesn't attribute to each of the disturbance types themselves. So right now we're not trying to assess whether the impact of forest thinning directly, but we are trying to understand across the landscape, across the state, how forest thinning and other disturbances, they will be reflected within the carbon inventory.
Thank you, Ryan. I'd like to move to Jenny Blaker's follow-up questions, and they are, is there a way of distinguishing between carbon sequestration in mature and old growth trees versus newly planted trees? What impact does herbicides have when areas are logged and thinned versus prescribed burn versus wildfire? And differences between natural forest ecosystems versus plantations?
Yeah, just to pick that up again, generally we can say that our inventory really doesn't assess the impact of management. And those kind of like case-by-case assessments of management types will be done through the SB 901 report, which we're going to discuss in a separate workshop. So it's really important to note that the inventory really does these longer term time scale assessments of carbon stock and stock change, and doesn't really do the shorter time, like scales that look at particular management impacts and things like that. And I would again point people to the SB 901 activities and that listening section that was advertised earlier. So sign up for that, and you can ask your questions there.
Okay, at this point, we've answered the questions in both the chat, and I don't see any raised hands. Don't be shy if you have any questions about forests, shrublands. Please raise them here. You can either raise them in the chat or raise your hand and ask them to the forum directly. We have a question in the question and answer feature from Sam Davis. Does the IPCC support this general type of ensemble approach, and or has it been done in other places?
So under the IPC guidelines, there's a tier 1, tier 2, and tier 3 approaches. So this essentially would kind of fall under essentially the tier 3 component, though it is a little bit different than just using a standard single modeling approach. I think the IPC does promote more sophisticated approaches for taking inventories. So under that guideline, this would be appropriate with the IPCC. We're trying to essentially integrate multiple models. Each one of these groups that are producing different products, they have different underlying data that they're using, possibly different remote sensing data that they're using. The approaches that they are using are different. And the way they're, basically the knowledge that they're using, the particular aspects that they're emphasizing is different. So the idea here is that we want to collectively take advantage of all that diversity of knowledge. And we actually are excited that that there should be a fair bit of difference between these different modeling methodologies, because we know that any methodology will have inherent weaknesses and strengths. So by having a diverse group of products, we'll be able to assess all of them together and kind of get hopefully a more representative assessment of what carbon inventories look like across the state.
Thank you, Ryan. I think we're going to just, give it 1 or 2 minutes to just make sure that nobody is going to ask a question. In fact, one just appeared in the Q&A feature from Derek Young. Could you share a little more detail on the plans for the ensemble validation data set, such as the data sources that may contribute to it and how they'll be compiled?
Yeah, certainly. Yeah, so at the current time, we are trying to assemble a validation data set, and we've been working with both a number of different people. We've spoken to with the U.S. Forest Service. We're working with CAL FIRE. We're approaching different experimental forests within California, research groups. The idea here is to try to get a diverse set of field-based data that even expands beyond like FIA data. Regarding criteria, we're looking for above ground biomass or above ground carbon so that we can have something to compare to the various remote sensing or data products that we're going to be getting for the ensemble. Yeah, and regarding the validation data set, the idea here is that we know that some of these will be correlated to some degree in the sense that the products that we will be assembling, since many of them will be FIA based with their validation. The idea here is that they won't be using all the same different types of products or same different methodologies and such. So we're hoping that this validation data set will be somewhat independent, and we'll be able to evaluate just how well that these products are doing.
All right, last call for questions. Otherwise, we'll break for lunch, and we're going to be back here at 1 o'clock with the harvested wood products presentation, followed by other lands, developed lands, and wetlands. So everybody have a good break, and we'll see you back here at 1 o'clock.
Right, welcome back, everybody. Good afternoon. My name is Dr. Kelsey Brewer, and I will be presenting CARB's work on the harvested wood products component of the Natural and Working Land Carbon Inventory 2025 update. CARB is the state's lead climate change mitigation agency and is tasked with tracking California's progress to meet its targets of carbon neutrality by 2045. On this slide, you can see a simple equation that describes how CARB is thinking about carbon neutrality. Carbon neutrality is achieved when any combination of the state's emissions and removal sources combine to equal zero or below. This includes the state's AB 32 sources, those from fossil fuels, landfills, dairies, natural and working lands emissions and removals, and any other carbon removal pathways. Natural and working lands have a plus minus here because these lands can either be sources or sinks of atmospheric carbon. To quantify the contribution of lands towards carbon neutrality, CARB must assess the effect that climate, wildfire, droughts, pathogens, management, or anything else may have to impact plant and soil carbon stocks. This tracking of land-based carbon stocks is achieved through our Natural and Working Lands Carbon Inventory. Harvested wood products vary in composition, use, disposal rates, and subsequent carbon retention lifespans. Short-lived harvested wood products like bioenergy feedstocks and biofuels are consumed soon after production, offering temporary carbon storage due to their rapid turnover. Soil amendments such as biochar, compost, and mulch store carbon for durations ranging from short to long term, depending on decomposition rates and application methods. Pulp and paper products are generally short-lived, with items like newsprint and packaging disposed of quickly. However, durable items like books may persist longer, and landfill-deposited materials can retain carbon for decades due to slow decomposition rates. Long-lived harvested wood products such as plywood, panels, and lumber used for construction or furniture store carbon for decades or longer. These materials contribute significantly to long-term carbon storage and are often recycled, extending their lifespan and utility. Production of harvested wood products is closely tied to land use and management practices across California's landscapes. The state faces significant challenges in achieving its wildfire, climate, and resilience goals, made only more complex by the need to make productive use of the large volumes of woody biomass generated through vegetation treatments. Land management activities, including those outlined in California's AB 1757 Nature-Based Solutions climate targets, will influence carbon flows into harvested wood products. These targets present a mix of impacts, with some increasing biomass harvesting and others reducing it. But overall, a net increase in annual wood harvesting is anticipated as these initiatives are implemented, contributing to greater carbon stock accumulation within the wood product sector. The newly released 2030 and 2045 targets include fuel reduction activities such as thinning and uneven age timber harvesting, as well as afforestation, elongating harvest rotations, and adjusting harvest intensity. These combined efforts will significantly alter the volume and characteristics of harvested woody biomass over time. Additionally, percentage-based targets aim to limit forest land use conversion, reduce catastrophic wildfire, and enhance the resilience of communities and surrounding ecosystems. Different wood feedstocks have distinct characteristics that determine their suitability for various applications. Sawwood, typically derived from large diameter, high-quality trees, is relatively dense, strong, and durable, making it ideal for structural uses like lumber and plywood. Pulpwood is smaller and less structurally sound, though is suitable for paper, cardboard, and pulp products due to its fiber properties. Thinning residues from logging or fuel load management are smaller, irregular pieces, often with lower density and higher moisture content, making them more suitable for bioenergy, biofuels, or soil amendments. Notably, as fuel load management efforts under the nature-based strategy targets expand the availability of this particular feedstock, emerging technologies will aim to utilize these materials in products ranging from engineered mass timber products to cellulose nanomaterials used for water treatment, food packaging materials, as a replacement for plastic, and a host of other values. Standing dead trees, known as snags, and other types of dead wood have usability depending on decay levels, which affects their energy content and applications. While social benefit of mobilizing these materials out of the forest is assessed on a case-to-case basis, they otherwise provide essential ecological benefits like wildlife habitat and nutrient cycling. Lastly, urban wood waste adds variability to the feedstock pool, offering recycled or repurposed options for energy production and manufacturing. Neither the 2018 Natural Lands and Working Lands Carbon Inventory nor CARB's SB 901 report have previously included harvested wood product estimates. However, they have emphasized the need to estimate and monitor carbon stocks within this pool, as changes in land management and industry practices iteratively influence wood product harvesting and utilization over time. This figure estimates the carbon flux between the atmosphere and forest and rangeland biomass, showing both carbon stock changes and emissions. In addition to highlighting both California's total forest emissions and sequestration, the diagram also shows the role of forest management in transforming carbon, resulting in a broad range of 1.9 to 7 million metric tons of carbon per year. The rightmost section, outlined in red, highlights uncertainties surrounding the carbon released or retained in harvested wood products, a key question this inventory section aims to better understand. In the 2025 inventory update, CARB will implement the Harvested Wood Products Carbon Model, a tool used to estimate the carbon dynamics associated with harvested wood products over time. This model allows users to track the flow of carbon from forests and other harvested land types into various categories of wood products and accounts for how these products store or release carbon throughout their life cycle. Carbon stocks are calculated cumulatively, considering the variation of carbon stock persistence across various harvested wood product types. By providing a quantitative framework, the harvested wood product carbon model helps assess the role of harvested wood in carbon storage and its contribution to greenhouse gas inventories through tracking from harvest, product use, all the way through eventual disposal and carbon stock loss from landfill decay or combustion. The harvested wood product carbon model was originally developed for the U.S. Forest Service, and a later version has since been updated for California's specific context through a partnership between CAL FIRE, Oregon State Department of Forestry, University of Montana, the U.S. Forest Service, and Groom Analytics. The harvested wood products carbon model has traditionally used the IPCC production approach, shown here in the left figure, which tracks carbon dynamics of harvested wood products from timber harvested domestically within California. This method calculates carbon stock changes based on forest growth, harvested wood production, and the decomposition or combustion of domestically grown wood products, but excludes imported wood from its scope. Exports are theoretically tracked with this method, but the focus remains on wood produced within the jurisdiction boundaries. Instead, CARB will be implementing the IPCC stock change approach, shown in the right figure. This approach uses a consumption-based system, tracking carbon stocks of all harvested wood products consumed within a jurisdiction, regardless of their origin. This approach still calculates domestic harvested wood production, but adjusts stock changes by including both imports and excluding exports, with a focus on the carbon embodied in consumed wood, including emissions from its decomposition or combustion. While the production approach is useful for monitoring the specific outcomes of harvesting from California forests, it lacks the ability to track large portions of harvested wood products flows throughout the state, as at this point, a large plurality and perhaps even the majority of existing harvested wood products within California have been imported. Importantly, this approach still allows CARB to isolate and monitor the harvest and use of domestically produced wood products. This schematic outlines fixed assumptions and processes underlying the current harvested wood product carbon model version. The purple boxes highlight fixed assumptions influencing the carbon accounting, while the yellow boxes identify the sole variable input, the annual raw timber harvest from California forests. This model uses fixed ratios to estimate timber product formation, such as saw logs and pulpwood, as well as conversions into primary products like lumber and paper, and final end-use products like furniture and building materials. It assumes fixed decay rates for landfills, national or regional averages for production efficiencies, and specific half-lives and discard ratios for harvested wood product categories, which determine how long carbon remains stored before released through decay or combustion. These assumptions, based on historical studies, do not fully account for local variations, market trends, or technological advancement. This model simplifies calculations, but cannot dynamically adjust changes in recycling practices or product use. And for the natural and working lands inventory, which tracks carbon stocks rather than emissions, the harvested wood product carbon model provides two key outputs, shown here in red boxes. One, total carbon for harvested wood products currently in use, and two, total carbon for harvested wood products residing within solid waste disposal sites. Accurate allocation of harvested wood products across categories and stages of processing is essential to tracking carbon stocks. CARB aims to update the harvested wood product carbon model by integrating empirical data, highlighted here in the yellow boxes, to replace existing fixed assumptions. By incorporating detailed production data for primary and end-use products, the model will better reflect actual market outputs, enhancing carbon storage estimates. Accurate recovery data, including recycling rates, will allow the model to account for product lifespans and reduce emissions from disposal. Refined disposal rate information, such as proportions of products sent to landfills, energy generation, or composting, will improve carbon flux estimates. These updates will replace generic assumptions, making the model more reflective of real-world conditions and strengthening its role in policy and climate mitigation analysis. To improve the harvested wood product carbon model's accuracy, CARB is reviewing and, where appropriate, updating remain fixed variable assumptions. Conversion factors, which translate timber volumes into carbon content, need reevaluation to reflect species-specific variations, especially between hard and softwoods, and changes in wood densities due to management and climate factors over time. The photo on the right shows how wood densities for redwood have changed over time due to selective harvesting and faster growing tree species with lower densities. Pulpwood and wood product loss ratios should also be updated using recent data from mills to account for technological advancements and efficiency improvements. The main update focus is on decay half-lives, which determine the rate of carbon release after disposal. These are currently being reassessed based on empirical studies that consider changes in product durability and landfill practices. The model currently assumes all landfill carbon loss follows first-order decay rates, but decay actually occurs in multiple phases, such as aerobic, anaerobic, and methanogenic, each with different rates. Climate factors such as precipitation and temperature also influence emissions from landfills, which results in notable regional differences than the current model reflects. Improving the accuracy of model outputs depends on the quality and disaggregation of empirically measured data. Data must be broken down by material type, for instance, distinguishing between newspaper and cardboard. Otherwise, the natural and working land carbon inventory cannot account for differences in carbon fate. Generally, the most accurate available data for harvested wood products is economic production and trade data sets. The harvested wood product carbon model can integrate data from various sources to enhance its accuracy and replace these fixed assumptions. However, most data sets come with limitations that must be addressed, generally through cross-referencing multiple similar data sources. For instance, domestic production data can come from the U.S. Forest Service timber product output reports, which are limited by their reporting interval, but can be combined with CDTFA timber yield tax harvesting statistics, which have more frequent reporting periods, though limited data product disaggregation. Domestic trade data estimates can be drawn from the U.S. Census Bureau's Commodity Flow Survey and trade association data like the Western Wood Products Association lumber statistics, which, while having limited public availability, should provide adequate temporal coverage. International trade can be found from USITC trade data reports, though this requires some additional assumptions, such as regional distribution after port of entry. Where empirical data gaps remain for both domestic and international trade, the regional economic model gravity modeling approach can predict trade flows between two jurisdictions based on their size and distance from one another. This model predicts the volume of trade between two areas as proportional to their economic size. It also predicts that trade is inversely related to the distance between these two areas. The model controls for other factors that may affect trade, such as price differences. For end-of-life data, CalRecycle's recycling and disposal reporting system tracks landfill, disposal, and recycling rates, though the reliability of this data may vary based on regionally specific reporting limitations. Data tracking limitations will likely lead to some underestimation of harvested wood product carbon stocks, as much of the available data starts in the early 2000s. While some domestic production data exists dating back to the 1950s, much of the trade activities prior to the 2000s will likely be underreported. Infrequent reporting, limited product disaggregation, and challenges in accessing trade data may further hinder accuracy. While the model's assumptions are currently being updated, we will continue to be limited in modeling harvested wood product utilization and decay variations occurring based on local sociocultural and economic factors. Current efforts are focusing on integrating all available empirical data sets for harvested wood products, including production, import, export, discard, and recycling data. CARB is collaborating with CAL FIRE, the U.S. Forest Service, and academic partners to improve the model's accuracy, particularly for carbon conversion factors and decay rates. Additionally, the model currently lacks spatial allocation, meaning we don't currently understand where harvested wood products exist across the state. Future efforts will address this using remote sensing techniques to map the harvested wood product carbon pool across California's built environment. And with that, thank you. We will now welcome questions from the audience. To ask a question, please use the raise hand function. The host will call your name and permit you to talk once it's your turn. You can also submit written questions using the Q&A feature or at any time after this meeting by submitting via our public website or the email address on this slide.
Thank you for that talk on the harvested wood products, Kelsey. I also want to remind everyone at this point to try to keep your questions to around a minute or less, though everyone who's asked questions publicly in the forum seems to have done a pretty good job about keeping them concise. At this point, we have someone raise their hand, Gary Hughes. Gary, do you have a question or comment you would like to make about the harvested wood products?
Yes, thank you. My name is Gary Hughes, and I work as a co-director with the international organization Biofuel Watch. And just to recognize it's great that the Air Resources Board has come back to these matters again. I was looking through things, and it's 4 years ago now that there was an effort to follow up on SB 901. And then actually, I'm looking now, and I made a comment 4 years ago that still applies now, and that's basically to address the fact that the entire premise of climate benefits from supposed carbon sequestration and harvested wood products is highly speculative, and it fails to recognize the longevity of a pulse of carbon in the atmosphere and the brevity of carbon residence in a manufactured wood product. The granting of a carbon sequestration value to harvested wood products is actually translated in real life to a get out of jail free card for the timber industry. And then frankly, if such a value is to be assigned, it must be recognized as an anthropogenic carbon pool. It's no longer forest carbon. Once the carbon is out of the forest, it is no longer forest carbon. It is no longer land sector carbon. So we need to remember that anthropogenic carbon pools are notoriously impermanent. A stack of lumber is an anthropogenic carbon pool similar to how a giant tank full of petroleum is an anthropogenic carbon pool. So these are, in essence, nothing more than delayed emissions. So it's great that the Air Resources Board has come back to these land carbon issues again, but it is a long time now that we've been struggling with the agency to actually really come to grips with the impacts from human economic activity on the landscape. So thanks for letting me make a comment.
Thanks for your comment, Gary. Yeah, I'll reiterate that the natural and working lands carbon inventory has a very specific goal and a very specific task, which is quantifying carbon stocks as they exist at a point in time. And so in that sense, it is the natural and working lands carbon inventory, and the working lands component does include various kinds of carbon stock assessments within developed lands, urban, in the built environment. And so using the harvested wood products carbon model and improving the accuracy of that over time, the goal really is to quantify the retention of carbon stocks in different harvested wood products over time. And as I said, the carbon retention in something like biofuels is drastically different than the carbon retention in something like timber or biochar. And so, our inventory methods aim to kind of capture that variability. I will also note just one more thing, which is that the natural and working lands carbon inventory does not, account for avoided emissions. So there's no counterfactual scenario analysis in terms of how wood could have been utilized in other ways, but instead it's just trying to capture wood utilization as it exists in reality.
Thank you for that thoughtful response, Kelsey. We have another question or comment from Maya Khosla. Maya, would you like to state your question or comment?
Yeah, hi, thanks. I actually have a few questions. I guess one of my, I'm going to try and wrap it real fast. I'm trying to keep in mind your time limitations. I guess the first question is, first, you're using models. How do they compare with reality, and how do you sort of standardize them with empirical information? That's number one. The second question is, how do you separate the product that goes straight toward biofuels and or biomass energy from timber when on the ground? That separation is quite tricky. I say this with experience. And third question is, are you aware of John Talbert's 2024 report stating that the state of California does not report or regulate GHG emissions from industrial logging. And is your quest, does that sort of include incorporating existing information and reports that have done some serious calculations where you are using models?
Yeah, thanks for your great and thoughtful questions, Maya. The first question, so the harvested wood products carbon model, the version R 1.1.0, that's currently applied in California, as I kind of presented on, has a lot of fixed underlying assumptions rather than being informed by direct empirical data or measurements. And so those types of assumptions include, kind of ratios of how harvested wood is distributed into primary and end-use products rather than direct measurements of where that wood flow is going. And so, yeah, again, as presented in the presentation, one of the major methodological updates that we're working on right now is replacing those fixed assumptions with direct empirical data. And that direct empirical data for this iteration of the Natural and Working Lands Carbon Inventory will predominantly be economic trade data. So various sources of trade data that we will cross-reference against each other to try and ascertain the most accurate estimates of actual wood product allocation from domestic harvested wood in California. And then, of course, various products that are imported and excluding those that are exported. So yeah, the answer to the question is it has actually been a tricky venture to back carbon stock estimates of harvested wood products with direct empirical data, but that is the task that we are mostly taking for this section. We welcome any resources that you think are useful and important for consideration. You can see where you can submit that information to us through our website or directly through email. We certainly are always trying to incorporate, the most modern data sets and most modern considerations. And I just will reiterate one more time that the Natural and Working Lands Carbon Inventory is a very specific task. So this does not represent all of CARB's work on harvested wood or biomass. This is very specifically a quantification methodology that is aiming to quantify the carbon stocks within harvested wood products of different types inside of California's boundary.
I can also jump in to answer that second part of the question about the John Talbert's 2024 report and whether or not or to what degree CARB takes into account logging effects on greenhouse gases. And we manage two pertinent inventories related to things like logging. One is our AB 32 inventory, which looks at industrial activities and landfills and things of that nature. And then we have our carbon inventory, which looks at the exchange of carbon and the change in carbon stocks over time on our land base. And related to that, the SB 901 report, which does take into account, it's tasked with taking into account different forest management activities, including clear cutting and logging. So we do take into account the effects of forest management in our SB 901 report specifically, and then related activities with machinery and things like that, and greenhouse gas emissions associated with operations of forest management in our AB 32 greenhouse gas inventory.
Thank you for that thoughtful response, Kelsey and Chelsea. We have another question or comment from a Gary Hughes. Gary, would you like to tell us what question or comment you have?
Yeah, thanks. Again, this is Gary Hughes working with Biofuel Watch, and I'm kind of double dipping. So thanks so much for your patience. I appreciate the work that's being done and follow up to SB 901. So I hope we can keep it going. I felt compelled, though, to say one thing really quick because I quickly looked at some of the slides again, and I wanted to flag there was an early slide that actually kind of made reference to an energy product from woody biomass with a photo of a gas pump. So that, the insinuation of this idea that we can make liquid fuels from woody biomass. And it's really way past time for the Air Resources Board to abandon this unicorn. Again and again, we've seen millions of dollars of public money put into trying to make a liquid fuel from woody biomass, and it doesn't work out. So can we get away from that? Because again and again and again, the Air Resources Board brings it up, and it's a horrible distraction to the work that really needs to be done. So thank you.
Yeah, thanks for your comment, Gary. Yeah, I mean, you know, there are various utilization pathways for harvested wood, as you know, you are alluding to. And those various pathways are at different stages of technological development. I'll just reiterate one more time that, you know, that the Natural and Working Lands Carbon Inventory is really just a carbon stock-based methodology to calculate, you know, where carbon is at a given time period. So this you know, assessment is not directly related to any kind of policy implications with respect to where wood should go, but more just quantifying where it is actually moving on the ground. So yeah.
Thank you, Kelsey. I think what we're going to do is, before we get back to Maya for a second time, I'd like to go to a comment in the question and answers written by Jenny Blaker. As I understand it, you are saying that the updated inventory will exclude wood exported from California. I'm thinking about the 1 million tons annually proposed to be exported in the form of wood pellets to Asia and Europe. How would the carbon loss from California forests be accounted for in this scenario?
Yeah, great question, Jenny. And I think that that's an area to, you know, kind of visit and make sure that that's clear. So the quantification method for the harvested wood products section will quantify domestically produced wood within California boundaries. It will also quantify the wood that is being imported, and it will quantify the wood that is being exported. So all these various categories of carbon stocks associated with harvested wood and their flows will be quantified, and that information will be available. But what I mean to say when we are excluding exports is that you know, we are doing a carbon stock assessment of the carbon within California boundaries, which requires that we exclude the carbon that leaves the boundary area in the form of exports. And so that's what I mean to say is simply that you know, that exported carbon that is residing and being consumed elsewhere outside of California will not be part of California's carbon stocks, but we will be quantifying that export, which will give, you know, important insights into kind of domestic production and the flow of that wood products over time.
Okay, I see that, Maya, you have a second question, but we're really getting close to the 1:30 time, and to stay on schedule, I think what we might want to do is wait a couple beats and perhaps move on to the next session, which would be for other lands. I think that's being given by Kyle Lunenberg.
Hey everyone, my name is Dr. Kyle Lenenberg. Today I'll introduce the methodology updates for sparsely vegetated ecosystems. And just to note, in this presentation, I'll use the term sparsely vegetated lands rather than the IPCC nomenclature of other lands. This is just to avoid confusion when referencing other land types versus other lands. Next slide, please. So if you've attended the other sessions today, you've probably already seen this figure, but CARB is the lead climate mitigation agency and is tasked with tracking California's progress to meet its target of achieving carbon neutrality by 2045. On this slide, you can see the simple equation that describes how we're thinking about carbon neutrality. Carbon neutrality is achieved when the state's AB 32 sources, those sources from fossil fuels, landfills, and dairies, plus or minus natural working lands emissions, minus any other sequestration, equals or is below zero. To note again, natural working lands have a plus or minus here because these lands can be either sources or sinks. To quantify the contribution of lands towards carbon neutrality, CARB must assess the effects of climate, wildfire, droughts, pathogens, management, and anything else that impacts plant and soil carbon through the Natural Working Lands Carbon Inventory. Next slide, please. So sparsely vegetated lands currently comprise approximately 10% of California's land area. These lands cover a diverse set of ecosystems that have less than 10% canopy cover. This includes deserts, beaches, dunes, bare rock, and areas covered in ice or snow. The primary drivers of change in these systems are land type conversion, disturbance, management, restoration, and climate. It's essential to note that many sparsely vegetated systems are slow to decay and slow to recover after an impact to their vegetation or soils. It doesn't take much to cause disturbances in these systems that result in long-term carbon stock effects. For example, biocrusts are biologically active top layers of soil in some sparsely vegetated systems. These crusts are critical for soil carbon stock stability, but can be disrupted by something as simple as excessive pedestrian access. Complete unassisted recovery from disturbance can take centuries, meaning actions such as conservation implemented today can effectively prevent long-term carbon stock vulnerability. Next slide, please. Alongside the National Working Lands Carbon Inventory, California set the most ambitious range of nature-based solutions targets in the nation, which includes all lands. For sparsely vegetated lands, these targets call for between 75,000 and 95,000 acres of increasing climate resilience every year between now and 2045. These targets include actions such as conservation and restoration. These targets affect action in sparsely vegetated ecosystems such as rocky summits, as shown in the top left photo, deserts and dunes in the center photo, and beaches, shown in the upper right photo, along with other systems. In developing an updated methodology for natural working lands, the Natural Working Lands Carbon Inventory, our methods must be able to track the implementation and carbon consequences of these targets. Next slide, please. Displayed is a schematic of the Natural Working Lands Carbon Inventory methodology for sparsely vegetated lands in the previous 2018 update. This relied on two primary processes to calculate existing carbon stocks, land, fire, sea, as shown in the bottom or the top half of this figure, and soil carbon model, as shown in the bottom half of this figure. Land, fire, sea quantifies total carbon, which includes live, dead, root, and litter pools. It does this by integrating empirical measurements of carbon density with land fire vegetation products, as shown by the gray data boxes. As with other empirically derived models, part of land fire sea's strength is that we can continue to update these underlying empirical measurements as new data becomes available. Since this was last updated in 2015, a substantial number of allometric equations have been published that enhance our methods. The soil carbon model quantifies soil organic carbon. The soil carbon model functioned by ingesting a third-party map of soil organic carbon across California, soil grids, and modified soil carbon stocks using calculated stock change factors. This previous methodology was already an improvement on IPCC default guidance, which assumes soil organic carbon is 0 in these ecosystems at tier 1 or tier 2 levels. However, using a global map of soil carbon limited our ability to quantify ecosystem and California-specific effects on soil organic carbon, such as biocrust disturbance. Next slide, please. Displayed now is the updated methodology we proposed for this iteration of the Natural Working Lands Carbon Inventory. There are still two primary components, land fire sea and a soil organic carbon model. I'll return to this figure a couple times throughout the presentation, but just to give an overview, major changes include an analysis of high-resolution aerial nape imagery, as shown at the top of the diagram, the incorporation of new literature biomass density values, as shown in the upper gray box, and enhancements to the soil organic carbon quantification, as shown in the lower half of this figure. These proposed updates provide a couple of benefits. As you can see, literature-derived allometric equations used to update land fire sea will first be associated with a NAPE analysis. Because allometric equations are usually published for individual plants, it's not appropriate to assume the raw data will scale to a 30 meter by 30 meter land fire pixel. The NAPE analysis, which I'll introduce later in the presentation, enhances our ability to implement these allometric equations and expands the pool of equations we can access. We will also build upon soil organic carbon models using a unified framework, again shown in the bottom half of this diagram. This unified framework ingests carbon training data and predictors specific to California's sparsely vegetated lands. This will enhance the inventory sensitivity to primary drivers of change such as disturbance and management. Next slide, please. To start, I'll cover the updates we propose for land fire sea and its underlying empirical data. Next slide, please. Displayed now are the literature-derived values for biomass carbon density synthesized and incorporated into land fire sea by Gonzalez et al. In 2015. This includes a range of sparsely vegetated ecosystems, which are shown on the left. Within the plot, you'll see the average total carbon in metric tons per hectare, including live, dead, below ground, and litter pools. To note, these are average values, and within the land fire sea model, canopy cover, canopy height, and disturbance modify these base values. In this update, we will add additional biomass carbon density data that has been published for sparsely vegetated communities since the last 2015 synthesis. This will primarily consist of allometric equations. Allometric equations relate measurable plant features such as canopy height or diameter to known biomass carbon densities. Allometric equations are most commonly published for individual plants. To connect these allometric equations with land privacy, it's important to know the density of individual plants within a remote sensing pixel. In the previous inventory, this density was indirectly calculated. In this update, we will use high-resolution aerial imagery to explicitly quantify density and other physiologic parameters of these plants that connect them with the synthesized allometric equations. Next slide, please. So, this update is shown in the proposed methods under the NAEP analysis box, which I'll now cover. Next slide, please. NAEP, or the National Agricultural Imagery Program, is a remote sensing product put out by the U.S. Department of Agriculture. When compared to satellite products, NAEP imagery has a much higher spatial resolution and a lower collection frequency. This imagery is collected every 2 years in California, providing high-resolution imagery for tracking change at those temporal scales. Within the proposed methods, NAEP will be used to enhance the connection between remote sensing data and allometric equations. It will also be used to track how management and disturbance affect canopy cover and other physiological plant features. Next slide, please. Here's an example of NAEP imagery and how it may be used to track canopy cover within sparsely vegetated systems. In the left 3 photos, you'll see aerial NAEP imagery of 3 different sites across California with differing canopy cover percentages. In the right 3 images, you'll see canopy cover percentage calculated as a normalized difference vegetation index, or NDVI threshold. An NDVI threshold uses spectral indices to quantify the percentage of vegetated pixels. In the right 3 images, white pixels denote areas that were detected as vegetation versus ground. So based on the IPCC definition of sparsely vegetated lands, the top row of photos are the only ecosystem to have less than 10% canopy cover, meaning these are sparsely vegetated systems. The other 2 rows of photos are classified as shrublands. As you can see, in these sparsely vegetated systems, it is much easier to track individual shrubs and explicitly quantify features such as their diameter, which can be directly connected to allometric equations for individual plants. This is one benefit of including an analysis of NAEP data. The other benefit is that NAEP data is collected every 2 years. If we can detect an individual shrub in one image, it is likely that we'll be able to track the life of that individual shrub over time. This allows us to much more directly quantify the effects of management and restoration in sparsely vegetated systems. Next slide, please. So the other half of the proposed updates, as already mentioned, relates to quantification of soil organic carbon. Across all land types from the Natural Working Lands Carbon Inventory, we propose a unified soil mapping approach which integrates digital soil mapping statewide while ingesting ecosystem-specific drivers of change. Next slide. As mentioned earlier during the soils methodology update presentation, all land types will use a unified soil approach which integrates a statewide data set and ecosystem-specific drivers of change to quantify soil organic carbon. Displayed is a 10,000-foot overview of this unified effort. Starting from the left, literature time series values of soil organic carbon are integrated into a statewide database. Digital soil mapping is performed using environmental drivers, management, and disturbance maps that are specifically tied to primary drivers of change for sparsely vegetated lands, as seen in the central panel. Once a digital soil map is developed, it can be applied to produce statewide maps of soil carbon over time, as well as quantify the uncertainty underlying our predictions, as seen in the right panel. Next slide, please. This effort will ingest all available soil organic carbon for sparsely vegetated ecosystems. However, it's critical to note that soil organic carbon data in these systems is still limited. On the right is a collected data set known as the World Soil Information Service, or WOSIS, which synthesizes available soil organic carbon data sets for ecosystems globally. When we look in California, we find that sparsely vegetated ecosystems comprise only 35 of the 3,000 soil core data points available for California. Updates to our methodology will explicitly quantify uncertainty given these challenges and make use of all available data. This update will also form a foundation which will enable future contributions of data and the inclusion of process-based modeling runs for management and disturbance, even though these data sets are currently very limited. Next slide. Other than the calibration and validation, Data, the Unified Soil Framework will use a combination of universal and ecosystem-specific predictors. Universal predictors include climate, vegetation, topography, and parent material. Ecosystem-specific predictors for sparsely vegetated lands will include biocrust disturbance, nape-derived management events, and current or historic land use change. Next slide, please. So, for example, biocrust disturbance is a critical component for modeling soil organic carbon within sparsely vegetated ecosystems. Biocrusts are biologically active layers of soil that affect soil organic carbon cycling and other co-benefits. These biocrusts form over long timescales, but can be easily disrupted by human activity. Activities such as recreation, development, land use change, and management can affect biocrusts, creating long-term carbon cycling consequences. Current research has demonstrated that biocrusts have a positive effect on soil organic carbon in many systems globally. A recent global meta-analysis found that biocrusted soils in drylands had 70% higher soil organic carbon on average when compared to uncrusted or disturbed soils. On the right is the data set we propose to simulate biocrust disturbance within the Unified Soils Framework. Biocrust cannot currently be directly remotely sensed, although there is promising research in the realms of hyperspectral satellite imagery. The proposed data set is called the Human Modification Index. This product has been produced for multiple years within the carbon inventory time period. It quantifies human modification, and in this context, biocrust disturbance, as a factor of human activities, including mining, off-highway vehicle usage, agriculture, development, and proximity to roadways. This data set will quantify the diffuse and difficult to detect disturbance that cannot be tracked with currently utilized products like land fire disturbance. Next slide, please. So in summary, the proposed methodological updates will enhance our ability to quantify both biomass carbon stocks and soil organic carbon stocks for sparsely vegetated ecosystems within the Natural Working Lands Carbon Inventory. The proposed updates build upon previous methodologies by integrating new literature-derived values of biomass carbon density, adding a high-resolution imagery analysis to connect those new features with broader spatial patterns, and by implementing a unified soil organic carbon framework that improves soil organic carbon estimates despite data limitations in these systems. To highlight the existing limitations and future directions for the Natural Working Lands Carbon Inventory, in this update, we did not find sufficient data, models, and literature to quantify soil inorganic carbon. In California's sparsely vegetated lands, inorganic carbon is a major portion of the soils. Historically, inorganic carbon has been assumed to interact with the atmosphere on extremely long timescales. However, nascent studies have shown that human actions, especially actions which disturb the soil profile or alter hydrologic cycles, can alter soil inorganic carbon on faster timescales. In compiling these updated methods, CARB staff reviewed the available modeling resources that may quantify effects of disturbance on soil inorganic carbon. We were not able to find an open source model with broad scale acceptance in literature that meets our criteria and could be supported by available temporal and spatial data sets. As IPCC does not provide default values for soil inorganic carbon within these systems, we were not able to incorporate this pool within this inventory update. Additionally, future tools which can quantify biocrust disturbance explicitly using remote sensing platforms with regular recurring timelines would be a benefit to the Natural Working Lands Carbon Inventory and enhance our quantification of related soil carbon effects. Next slide. So with that, we can open it up for questions or comments. As a reminder, here are the instructions. Please keep questions or comments to 2 minutes, and we'll give you a friendly reminder when you've reached that 2-minute mark.
Great, thank you, Kyle, for that wonderful discussion. Anybody has any particular questions or comments regarding sparsely vegetated landscapes, also known as other landscapes, please feel free to raise your hand. I've noticed in the question and comment section that Maya Khosla has some extensive comments about what land fire does or does not tell us. There's a lot of points that you're making here, Maya. Would you mind stepping up and kind of verbally condensing what the comments you've made and presenting them to our panelists so we could perhaps address the issues that you might be having? You should have the floor, Maya.
I'm sorry. I'm sorry. I will have to defer to writing those down and providing written comments. My apologies. I do have another meeting to go to.
Okay, well, we definitely welcome your feedback.
Thank you. Thank you so much.
We have another comment from Jenny Blaker, who says, can you comment on hydrologic cycles in forest landscapes and how they may impact carbon storage? Not sparsely vegetated landscapes, but I'm wondering about the carbon-water nexus.
Outside the sparsely vegetated land, so I'd be happy to open it up to the forest crew to take this one on.
All right. Like as said before, like on the timescales that the inventory is looking at carbon stocks, we're not looking at short-term relationships or any kind of like biophysiological model that's coupling water and carbon. We know generally that those are tightly coupled. Drought is one of the primary drivers of change that we have identified, and it will impact the carbon stocks in California overall. So we will see the impact of drought and water changes in the hydrological cycle on the landscape expressed in carbon stocks over longer periods of time as these patterns change in California and impact the ability of the landscape to retain carbon stocks or build carbon stocks up. But in the scope of the inventory, this is not a question that we're directly investigating or that the inventory can answer because we're just looking at different scales.
Yeah, just to reiterate what Matthias is saying, we do know that the hydrologic cycle in forests, they do impact one another. But as Matthias was saying, that's for the purposes of this inventory, we're not trying to directly model those connections. We're trying to quantify what the stocks are on the landscape. When we later on for processes such as the scoping plan, when CARB is trying to forecast forest carbon into the future, considerations such as the impact of hydrology, whether there's a lot of precipitation or not that much, all of those things come into play during that type of analysis. But for the inventory here, we're just trying to understand what is currently on the landscape throughout California. And that is used as essentially a baseline or can be used as a baseline for other analyses and such.
At this point, I invite anybody to step up and maybe ask any questions about sparsely vegetated landscapes for Dr. Lunenberg. Or if they want to, they can make a comment in the question and answer session. Okay, seeing no particular interest in asking further questions or comments regarding sparsely vegetated landscapes, I think we're going to take a quick break and then we'll return at 2 o'clock. We will be discussing developed lands at that time. Thank you.
All right, good afternoon, everyone, and welcome back from the brief break. We're going to go ahead and get started on the next presentation. I'm Dr. Tara Seeley, and today I'll be presenting the proposed methodology for our natural and working lands carbon inventory within developed lands. Next slide. If you've attended other sessions today, you've probably already seen this figure. But as a reminder, California has an ambitious goal to reach carbon neutrality by 2045. This schematic illustrates multiple categories of carbon that will all count towards this carbon neutrality. The center term is what our natural and working lands carbon inventory focuses on. The inventory's goal is to quantify the carbon stocks in natural and working lands over time and with sensitivity to specific drivers. So today I present updates to the quantification methodology, which was last implemented in 2018, and I'm looking forward to hearing your feedback and suggestions. Developed lands consist of residential, transportation, commercial, and production infrastructure of any size. As you can see in these images, CARB's definition of developed lands is rather expansive and extends beyond urban areas and suburban areas to really any place where humans have built structures, installed energy infrastructure, and roads, including but not limited to rural areas and the wildland-urban interface. You can see in the map the webbed red lines that extend throughout California's landscape all constitute developed lands, with a statewide area totaling 6.8 million acres. Compared to other landscape types, developed lands are the most intensively managed and modified lands with the highest density of people. Mapping or delineating developed lands is somewhat complex since it includes multiple different types of infrastructure. In terms of delineating developed lands, we are building upon the 2018 carbon inventory methods in two key ways. First, we are using the term developed lands now instead of settlements to reflect the multiple land uses that are encompassed in this land type. Second, instead of using land fire classification, we will map developed lands by merging spatial data on energy infrastructure, roads, nighttime lights, and building footprints. Merging these data sets will help us more comprehensively delineate all developed lands. I'd also like to draw your attention to the third bullet point, which states that quantification of carbon in some developed land areas may actually require methods for other land types. So as an example, consider a road winding its way through forests in the Sierras. The land cover that dominates in that roadside region is forest, and therefore forest methods are the most appropriate for quantifying carbon in that specific location. However, the land use of that area is still considered developed lands. So in this case, the carbon that has been quantified alongside the road will ultimately be attributed to developed lands in our inventory. The decision of how to quantify carbon ultimately relies on using the methodology that is considered most robust for the location, but our inventory process still enables us to report just how much carbon is stored within our developed lands boundary. Next slide. Shown is an alternate figure depicting CARB's formula for carbon neutrality. Another important distinction about developed lands is that besides natural and working lands, there are other sources and sinks illustrated in the diagram, like transportation and direct air capture. These sources and sinks will likely occur within the developed lands boundary. However, they are not part of our natural and working lands carbon inventory. The scope of the carbon inventory is specific to quantifying carbon stored in the landscape's plants and soils. Carbon stored in developed lands is found in soils, herbaceous biomass, and woody biomass that are part of the grasses, shrubs, and trees. These pools can take the form of urban parks, gardens, private yards, street trees, and other forms of green space. In many cases, these carbon pools are relatively durable and resilient because they tend to be intensively managed and protected from risks like drought. The proximity of green space to people also provides communities co-benefits such as improved physical and mental health, urban cooling, and reduced energy costs. Carbon dynamics in developed lands are affected by a multitude of drivers. Climate change, drought, and development, for example, all threaten the resilience of carbon stocks in developed lands. The management changes established by AB 1757's Nature-Based Solutions, or NBS, climate targets can also potentially influence carbon stocks in developed lands. So this table shows the NBS 2045 climate targets. Acreage-based targets consist of afforestation between communities and croplands, which helps reduce community exposure to pesticides, conservation, which helps preserve existing green space, and urban and community greening, which aims to expand tree cover and green space in developed lands. I also want to highlight that in addition to AB 1757, there is AB 2251, which is a bill that sets a target for a 10% increase in urban canopy cover by 2045. These nature-based targets here are more specific, yet still consistent with that goal. In addition to increases in tree cover, mitigation of wildfire risk is also an emphasis of the developed lands NBS targets, reflected in the acreage-based target for reducing community wildfire risk by increasing defensible space, as well as the percentage-based targets aiming to decrease fire ignition caused by vehicles and to treat roads functioning as evacuation routes. Lastly, there is a tree-based target for increasing the number of trees in communities. These targets are intended to foster resilience, not only in developed lands green spaces, but also in our communities. One of our main goals in the Natural and Working Lands Carbon Inventory is to develop methodology which is sensitive to the impacts that these NBS management strategies may have on carbon stocks. Although the developed lands cover a wide extent, CARB's developed lands carbon quantification methodology is constrained by the spatial extent of available data. For this reason, developed lands carbon quantification methodology is limited to census-designated urban areas. These regions require unique methodology because, unlike other systems, urban green spaces are intensively managed, they can be irrigated, and they include almost no dead biomass. And they're also composed of exotic species that are not common elsewhere in California. Although urban-specific data is limited to these census-designated urban areas, developed land carbon beyond these urban areas is still quantified. It just uses different methodology. So there are two carbon pools quantified by developed lands methodology: tree biomass and soil carbon. Tree biomass, back to one slide, thanks. Tree biomass consists of carbon stored in trees, and it requires knowledge about tree species and tree cover to calculate. The previous 2018 inventory used randomized point samples applied to satellite imagery of urban areas. Each point was manually evaluated for whether or not it overlapped with tree cover. The proportion of points overlapping tree cover was then assumed to represent the relative tree cover in that urban region. We now have access to remote sensing derived tree cover, which is more comprehensive and much faster to evaluate. This is a flowchart of the proposed methodology for quantifying the carbon stored in tree biomass. As a reminder, this methodology is specific to census-designated urban areas due to the coverage of available data. Input data is highlighted in green, analysis steps are in blue, and the resulting outputs are colored in orange. So I'll go ahead and walk through the flowchart step by step, starting with the analysis in the top right. So the first step involves coupling urban forest inventory data with species-specific carbon allometry. The distribution of urban forest inventory data points is pictured in the map on the left. The inventory consists of almost 8 million trees, which is an 8-fold increase from the tree samples used in the 2018 carbon inventory. Species-specific allometry is derived from a tool called iTree, which just updated allometric equations as of 2021. These allometric equations translate the species and diameter of each tree into a carbon content. We will then connect this information on the species assemblage and carbon content to measurements of tree cover derived by matching tree samples to the U.S. Forest Service urban tree cover map. So this analysis will be conducted for each urban region to derive a regionally specific carbon density by canopy cover. We separate the analysis by urban region because different climatic zones tend to have different species assemblages, and it's important to represent that variation in our analyses. After deriving the regionally specific carbon density values, we will move on to step 2. Step 2 uses the U.S. Forest Service urban tree cover dataset. This dataset is 1 meter by 1 meter map of tree canopy within census-designated urban areas. Pictured here is an example of the data from the 2018 dataset over an image of Sacramento. The yellow denotes mapped canopy cover, and you can see how it overlaps with trees shown in the satellite image. Our updated methods will leverage this data set for 2012, 2018, and 2022. This is another key feature of our updated methodology because this tree cover data is sensitive to changes in urban canopy, which we anticipate to change as a result of the nature-based strategy targets. This tree cover data will be used to scale the regionally specific carbon density estimates to the full extent of tree cover in urban areas. The result from this analysis will be a spatially explicit distribution of tree biomass carbon within urban areas. The second carbon pool we quantify within developed lands is soil carbon stored within the top 30 centimeters of soil. Soil carbon in the developed landscape is affected by various drivers, and some drivers are common to most systems, which include soil type, climate, and vegetation. But other drivers are more unique or relevant to developed lands specifically, including whether soil is sealed under pavement and what type of land use history or disturbance has occurred. The approach towards quantifying soil carbon in developed lands is consistent with the unified soil carbon quantification framework employed by all the land types. Step one of this approach is to rely on process-based models to produce time series of soil organic carbon at various sample points. These temporal sequences are depicted by the tiered cylinder in the schematic on the left. Time series sample points will be distributed across the state and used for training data for the next step. The next step consists of digital soil mapping, relying on spatial maps of environmental covariates and management and disturbance data fed into a machine learning algorithm. The result will be a spatial distribution of soil organic carbon across the state. Since the soil approach was covered in a prior presentation, I'm going to emphasize the aspects of this that are specific to developed lands. On the right is a simplified schematic of our process to produce time series estimates of soil carbon in developed lands. The first step of this framework involves classifying soil cover into 4 general categories. The sealed category encompasses areas where soil is paved or impervious, derived from the National Land Cover Database estimate for percent impervious surface. The remaining 3 categories depend on the vegetation cover of unsealed soil, either tree cover, which is derived from the U.S. Forest Service tree dataset, other vegetation, which is a catch-all for non-tree vegetation derived from NAPE imagery, or bare soil, which is unvegetated soil. You can see in the methodology workflow that there is a divergence in the workflow based on whether or not the soil is sealed. So studies have shown that soil sealing reduces the amount of soil organic carbon stored in the soil because the lack of water, air, and carbon inputs alter biogeochemical processes. A key feature in our proposed methodology is incorporating soil sealing as an important driver of soil carbon in the developed lands landscape. Sealed soil will be represented relatively simplistically. We will use initial soil organic carbon estimates from a soils database produced by the Natural Resources Conservation Service, coupled with sealed soil stock changes derived from peer-reviewed literature to estimate a time series of soil organic carbon. Unsealed soil will utilize ROTH-C, which is a simplified process-based model that incorporates inputs of climate, soil type, and vegetation cover, which then differentiates organic matter into pools with different characteristics and retention times. The pools are sensitive to soil texture, moisture, and temperature. ROTH-C is a simplified model, but it can be calibrated with good accuracy. ROTH-C is completely open source and has been well vetted by the scientific community. However, our use of ROTH-C will hinge on empirical measurements of soil organic carbon within the developed lands landscape. Efforts to compile these empirical samples of soil organic carbon are ongoing, and we do welcome any suggestions or leads that you may know of. So the output from this methodology will be a time series of sample points of soil organic carbon in developed lands, and this will produce the training data used in our statewide soil mapping efforts as they progress through this unified framework workflow. So let me just end by summarizing a few key new features of our proposed methodology, as well as highlighting needs we have identified to improve these methods. The updated term developed lands encompasses a wider variety of land use compared to settlements. This term better reflects carbon dynamics related to development and infrastructure. Additionally, counties will be considering these areas in new planning efforts. With this expanded definition comes a need to revisit and update methodology and, of course, improve data coverage. For soil carbon quantification, a key new feature we are adding to our methodology is differentiating between soil cover types. A need we have, however, is to collect empirical measurements so that we can be confident that we are accurately representing soil carbon in the developed lands landscape. In terms of tree biomass, the U.S. Forest Service tree cover map has been reproduced for 2012, 2018, and 2022. This will track changes in tree cover and help us establish a baseline for future nature-based strategy changes. The current tree maps are created within census-designated urban areas, so of course, a need for future carbon inventory efforts would be to expand this map into developed land regions outside of those areas. As it stands, of course, we will still quantify carbon in those areas, but we will do so using methodology from different land types, and then we will attribute the carbon to developed lands. And finally, the tree inventory has expanded nearly eightfold, which improves our understanding of the tree species assemblages in urban areas. A need we have identified is that the inventory can be skewed towards street trees because they are more accessible for inventory assessments compared to trees on private land. Street trees tend to be comprised of different species compared to trees on private lands, so this has the potential to produce a bias in our inventory samples. So moving forward, we'd like to address this bias by acquiring more data that represents the full diversity of tree species that exist in the developed lands landscape. So that concludes my presentation, and I'm happy to take your feedback and questions at this time. And so if you would like to make a comment or a question, please go ahead and do so following the instructions on this slide.
If anybody would like to have any questions for Tara, please feel free to step up and raise your hand. At this point, we have some questions in the question and answer feature. First one coming from Kong Tran. That is, it is great that we have the U.S. Forest Service urban tree cover data sets. How about grasslands and open spaces in lawn and residential areas?
Yeah, thanks. Thanks for submitting your comment. I think, I'm not sure. Okay, so I will address the lawn and residential areas first. So with our current proposed methodology, lawns will be factored into our analysis. The carbon stock that we quantify in terms of biomass, we focus on woody tree species, and the reason for that is that they comprise the most of the carbon found in biomass in developed lands. It's like a persistent, stock that's durable from year to year, and we also have available data to do so. So the lawns will be incorporated in the inventory, but in terms of their contribution to the soil organic carbon piece of developed lands. And in terms of your question about grasslands and open spaces, provided those open spaces are within the developed lands boundary, we will again be incorporating that into our analysis.
Great, thank you very much, Tara. We have another comment from Christopher Black in the form of a question. Have you assessed how sensitive this developed lands approach is to the spatial resolution of the analysis? I'm curious if it's higher or lower than for other land use types.
Thanks for your question, Christopher. So our spatial resolution, again, is dependent on the input data that we use for our analysis, and depending on data availability, that can differ between land types and also even within a given land type. So I would say the tree cover map that we have for developed lands, it's 1 meter by 1 meter. This is very high resolution that it's higher spatial resolution than available data that we have for many other land types. For soils, some of the data we rely on is at 30-meter resolution. So it really just kind of depends on what pool we're looking at, what's available, but we do strive to maintain high spatial resolution. I will just say that the purpose and intention and goal of the natural and working lands inventory is to make sure that our carbon quantification is going to be relevant to the county and statewide scales.
Thank you, Tara. We have another comment/question from Christopher Black, and he asks, have you assessed how sensitive this developed lands approach is? Oh, sorry, I apologize, went to the other one.
Okay.
How about one from Chuck Mills? And he asked, will urban trees greenhouse gas reduction calculations go beyond sequestration and storage and evaluate avoided emissions from energy savings?
Yeah, thanks, Chuck, for that question. For the natural and working lands inventory, we do not try to calculate avoided emissions. To calculate avoided emissions, you need a bit of a different framework in terms of understanding what a counterfactual scenario would be. So the scope of the natural and working lands inventory is really just quantifying the carbon stock that exists at a point in time on the landscape, and tracking how that changes, over time as we periodically repeat and update the inventory.
Great, thank you, Tara. And finally, we have another question/comment from Jenny Blaker. And she asks, can you consider urban development, buildings and building materials, as well as urban trees and soils? For instance, concrete apparently emits greenhouse gases, while solar roofs and/or cool roofs can help reduce them.
Yeah, thanks, Jenny, for that question. So in terms of considering urban development, buildings and building materials within the developed lands land type, those are not carbon pools that we factor. We focus on what's stored in trees and soil. And part of the reason for that decision is we really align ourselves with the IPCC, or Intergovernmental Panel on Climate Change framework, which uses this natural and working lands inventory to focus on the biomass and soil pools. That being said, there are other teams at CARB that do tackle, some of those pools. So I would say CARB as a whole has work in that sphere, but it's not something that we are incorporating into our inventory right now. And as far as your second question, I'm just reading it here. Right. So again, that also applies to whether or not we, factor different materials. It's just not within the scope of what this, land type examines for the inventory. Thanks.
Does anybody else attending have any remaining questions for Tara regarding calculating the carbon inventory for developed lands? You can either raise your hand or you can place your comment or question in the question and answer feature. Okay, seeing no other inquiries in either the question and answer feature or raised hands, I think we're going to take a short break before we begin the final session, which will be dedicated to wetlands, and that'll be led by Kyle Lunenberg. Thank you. And that will begin at 2:30.
Hello, everyone. Again, my name is Dr. Kyle Lenenberg. Today, I'll present our final section, the proposed methodological updates for wetlands in the Natural Working Lands Carbon Inventory. Next slide, please. If you've attended our other sessions today, you've already seen this figure. CARB is the lead climate mitigation agency and is tasked with tracking California's progress to meet a target of achieving carbon neutrality by 2045. On this slide, you can see the simple equation that describes how we're thinking about carbon neutrality. Carbon neutrality is achieved when the state's AB32 sources, those sources from fossil fuels, landfills, and dairies, plus or minus natural working lands emissions, minus any other sequestration, equals or is below 0. Natural working lands is a plus or minus here because these lands can act as either sources or sinks. To quantify the contribution of lands towards carbon neutrality, CARB must assess the effects of climate, wildfire, drought, pathogens, management, and anything else that impacts plant and soil carbon through the Natural Working Lands Carbon Inventory. Next slide, please. Wetlands currently comprise approximately 2% of California's land area. The figure on the right displays the current extent of inland, coastal, and delta wetlands throughout the state, denoted in purple. The relatively small proportion of wetlands compared to other land types is largely attributable to the fact that 90% of California's historic wetlands have been converted to other land types within the past 2 centuries. Other than land use conversion, subsidence and accretion, sea level rise, salinity, management, and restoration are key drivers of this system. These drivers interact to influence the carbon storage and emissions of wetlands. As with other land types, we follow IPCC guidance for inventorying wetland carbon stocks and greenhouse gas fluxes. Uniquely, IPCC provides methods to quantify methane and carbon dioxide flux rather than just carbon stocks for wetlands. The 3 IPCC-defined wetland categories we quantify for California are coastal wetlands, more commonly known as salt marshes, inland wetland mineral soils, which include vernal pool systems and mountain meadows, and re-wetted organic soils, which are largely restored portions of the delta. Next slide, please. Alongside the Natural Working Lands Carbon Inventory, California set the most ambitious range of nature-based solution targets in the nation, which include all lands. For wetland and seagrass ecosystems, these targets call for 12,000 acres of climate action every year between now and 2045. Targets include actions such as conservation, restoration, and sea level rise protection across California's wetland and seagrass communities. These communities include ecosystems such as vernal pools, coastal wetlands, and eelgrass communities, as shown in the 3 photos. In developing an updated methodology for the Natural Working Lands Carbon Inventory, our methods must be able to track the implementation and carbon consequences of these targets. Next slide, please. For the 2018 Natural Working Lands Carbon Inventory, all wetlands used an IPCC Tier 1 approach. Emissions factors used in Tier 1 methods are globally derived parameters, thus previous inventory efforts had limited sensitivity to California-specific drivers of wetland carbon cycling and lacked the additional functionality of something like a Tier 3 process-based modeling approach. Historically, the lack of sufficient models, data, and mapping resources prevented the inclusion of wetlands at a higher methodology tier. In 2024, the California Ocean Protection Council, in collaboration with CARB and Windward Sciences, produced a white paper assessing the available biogeochemical models to include coastal wetlands at a Tier 3 IPCC methodology. Of the assessed models, 2 stood out as fitting the criteria set forth by CARB. To note, there remain systems for which we do not have sufficient information, including seagrass meadows, estuaries with dynamic ocean inlets, and heavily degraded wetlands that experience overriding human-based influences. Next slide, please. Here's a diagram of how carbon stocks and greenhouse gas fluxes were calculated for wetland ecosystems in the 2018 carbon inventory. This relied on emissions factors displayed in the top box. The statewide mapping that supported these calculations was derived from the San Francisco Estuary Institute's California Aquatic Resources Inventory, shown in the mapping box on the left. These 2 pieces provided the IPCC reporting for greenhouse gas fluxes, or GHGs. Soil organic carbon, as shown in the lower portion of this figure, relied on a third-party statewide map of soil carbon, soil grids, which quantified carbon stocks in the upper 30 centimeters of soil. Next slide, please. Here you can see the proposed methodology updates. I'll return to this figure a couple times throughout the presentation, but to give a brief overview, we propose updating the Tier 1 emissions factors approach with a Tier 3 biogeochemical model approach, as shown highlighted in blue. This will rely on additional geophysical, calibration, and validation data, along with maps and maps of vegetation and management, as shown by the gray boxes in this figure. We will also implement wetlands mapping using available data to make sure we track changes in extent and wetland type over time. There are a couple benefits to this update. Compared to an IPCC Tier 1 approach, California-specific models are much more sensitive to the primary drivers of change in wetland ecosystems. Enhancements to the mapping component will better describe changes related to sea level rise and land type conversion in all wetlands of the state. To note, in this update, we were not able to find sufficient modeling and mapping resources to model inland wetland mineral soils using process-based biogeochemical models. Inland wetland mineral soils will be included using an empirical model for soil organic carbon, as denoted by the Unified Soils Framework box, and emissions factors for greenhouse gas flux, denoted by the asterisk in the biogeochemical model box. To start, let's talk about the two models that we'll use in the proposed update. Next slide, please. The two proposed models are the Cohort Wetland Equilibrium Model, or SWIM, and the Peatland Ecosystem Photosynthesis Respiration and Methane Transport Model, or Peppermint. These are both process-based models, with SWIM modeling soil organic carbon and Peppermint modeling greenhouse gas flux of carbon dioxide and methane. In California, SWIM has been used to model changes in wetland carbon stock due to processes such as accretion of subsidence. Modeling these processes is critical for understanding wetland resilience to sea level rise and other drivers. Peppermint has already been parameterized for sites in San Francisco Bay and in the Delta, providing a basis for California-specific modeling of greenhouse gas exchange. This will enhance our ability to capture greenhouse gas flux dynamics when compared to the previous Tier 1 methods. An important note is that both Peppermint and SWIM models are point-based models and need to be scaled to statewide extents. For all land types within this update, we propose a unified framework to integrate process-based modeling and machine learning. This is depicted in the lower box of the figure. This framework was covered in the earlier presentation on soils, but to summarize, after running SWIM and Peppermint models at sites across the state with sufficient calibration data, we will scale these results using digital soil mapping. We will include wetland-specific covariates, anthropogenic factors, and soil forming factors in scaling model outputs. Next slide, please. So that section covered the process-based models that we will use to power this update. Now I'm going to cover the data required to support these models. First, looking at the required geophysical data. Next slide. Geophysical inputs for these models include tidal inundation, suspended sediment concentrations, climate, and water quality parameters such as salinity, sulfate, and nitrate concentrations. The primary data requirements are shown in the right callout box of this figure. Next slide. For geophysical data, datasets must be available at statewide extents, be sensitive to the primary drivers of change, and be open source. In these next two slides, I will demonstrate one of these datasets, our proposed data for tidal inundation, and how it meets these requirements to enhance quantification methods. The displayed picture is an aerial image of the Napa Sonoma marshes. As with many wetlands in the state, this area has complex tidal and topographic features that make it difficult to predict tidal inundation rates, a critical predictor of carbon storage and resilience to sea level rise. Next slide. In this figure, we depict the same area with remotely sensed tidal inundation. Green represents upland areas that are never inundated, and blue represents subtidal areas that are always inundated. This method relies on publicly available satellite imagery, such as Landsat and Sentinel imagery, to understand inundation patterns over wide temporal and spatial ranges. Whereas it would be difficult to model the complex interactions between tides, topography, and human structure across all state wetlands, remotely sensed data directly quantifies tidal inundation. The underlying data and models are open source with minimal latency. This means that future iterations of Natural Working Lands Carbon Inventory will automatically include updated tidal inundation as it changes from sea level rise and management. To note, we will use literature values of tidal inundation topography for the parameterization of process-based models, at calibration sites. Remotely sensed tidal inundation provides a scaling predictor, which allows us to expand calibration sites to statewide extents, but it's less appropriate for parameterization when directly sampled data exists. Next slide, please. So that's the geophysical data that will be ingested by these models. The other required input data is accurate maps of wetlands and how they change over time. Next slide, please. So our goal for wetland mapping is to create a product that is sensitive to land type conversion, accurately depicts vegetation cover, and incorporates restoration and management activity. This effort will combine the available mapping data sets for wetland extent, land type, restoration, management, vegetation community, and biomass control parameters, as shown in the right callout of this feature. This includes, there we go, thank you. This includes mapping resources such as NOAA's Coastal Change Analysis Program and San Francisco Estuary Institute's California Aquatic Resources Inventory. Next slide. Finally, the last part of this framework is the calibration and validation data we will use to parameterize these models and quantify our uncertainty. Next slide. Calibration and validation of soil carbon stock modeling, we will rely on the Coastal Carbon Atlas. This effort synthesizes wetland soil core data globally and collects it in a unified database. In the displayed figure, colored circles denote the number of soil cores available in different regions across the state. Please note, this does not display the entire extent of soil core data to be used in the proposed update, just those data used for process-based modeling, calibration, and validation. For coastal and delta wetlands, we will include additional empirical soil carbon data for inland wetland mineral soils, which is not displayed in this figure. Between coastal and delta wetlands, there are approximately 350 soil cores available. These cores are all stratified to multiple depths, which facilitates the parameterization and calibration of process-based models. Next slide, please. For the calibration and validation of greenhouse gas fluxes, we will use eddy covariance data. Eddy covariance towers measure landscape scale fluxes, providing critical data sets for quantification of carbon dioxide and methane exchange. On the right is an example of an eddy covariance tower measuring these exchanges. In California, there are eddy covariance towers in the Delta, in estuaries of San Francisco Bay, and in Elkhorn Slough. However, there's not publicly available data or eddy covariance data for coastal wetlands outside of these areas, nor is there data for inland wetland mineral soils within California. This limits our ability to quantify and verify fluxes in inland systems and in wetlands at the northern and southern extremities of the state. Next slide, please. So in summary, the proposed updates to wetlands would build upon previous carbon inventory methodologies, including coastal and delta wetlands using Tier 3 biogeochemical models. These enhancements will be more sensitive to land use change, subsidence, accretion, sea level rise, salinity, management, and restoration. And to close, I want to outline some of the existing limitations and future priorities for the wetlands inventory methodology. The first is to reiterate that inland wetland mineral soils, including vernal pools and mountain meadows, still require additional resources to implement process-based modeling. These systems have far fewer data sets, models, and maps to support this kind of effort. The second note is that nitrous oxide is an active area of research for California's wetlands, but currently lacks sufficient data for inclusion in this update. Finally, there are still some coastal wetlands that we cannot include using the modeling framework. These include eelgrass beds, bays with dynamic inlets, and heavily impacted wetland systems. Given these limitations, we believe the proposed methodology provides a foundation to address these challenges in the future. Next slide. With that, we can open it up for questions or comments. As a reminder, here are the instructions on how to pose a question or to submit a comment. Please keep questions or comments to 2 minutes, and we'll give you a friendly reminder when you've reached that 2-minute mark.
Great, thank you very much, Kyle. And I'd like to welcome any wetlands enthusiasts in the audience to step up and ask Kyle a question. He's very knowledgeable about this subject. And we have one in the question and answers feature from Brandon Broach. And he says, hello, is dredging in the bay included in soil stock measurements? I ask because dredging may affect the wetland's ability to accrete soil to maintain its height with regards to sea level rise.
Yeah, thank you for the question, Brandon. So the question relating to how dredging fits in here, right? So currently the inventory doesn't include subtitle features. However, it does include effects of dredging where they affect tidal inundation. This is kind of part of the reason we propose this remotely sensed tidal inundation feature, because sediment deposition can be a pretty critical feature in kind of in accretion rates or kind of mitigation of sea level rise risk. So in so much as dredging affects tidal inundation, it will be accounted for in the change in dynamics in coastal wetlands, but it won't be directly quantified in the soil organic carbon stores below water.
Great, thank you very much, Kyle. At this point, we'd like to invite anyone else to step up. We see have another kind of follow-up question from Jason Sauer. To be clear, are you conducting tier 1 analysis for inland wetlands?
Sure, Jason, thanks for the question. So it's a bit between. So we are still relying on tier 1 emissions factors for inland wetland mineral soils. So this would be for carbon dioxide flux and methane flux. However, we are using a tier 3 model through the Unified Soils Framework and empirical soil core data for inland wetland mineral soils for soil organic carbon. So until such a point as we can find a process-based model to supplement that tier 1 emissions factor, we're still relying on those factors.
And we have a follow-up question in the question and answer feature from Adina Payton. Considering the missing data for validation and upscaling, does CARB have a plan to get such data?
Yeah, so you know, the data requirements of this type of update and process-based modeling are pretty extreme, and we are, as I mentioned, grateful for the Delta and San Francisco Bay and Elkhorn Slough towers, which Adina maintains, that provide the calibration validation. CARB does have a current contract out looking for calibration and validation data in other sites throughout California, but this isn't set yet. So yes, we're hoping to expand calibration and validation data through measurements that we conduct, as well as measurements that we may synthesize from available literature.
We'd love to entertain any additional questions or comments anyone might have about estimates of the carbon inventory in wetlands for Kyle. Please feel free to step up and ask whatever you would like to. At this point, I'd like to remind all the people attending the workshop. Actually, let me get to that point in a second. I think I saw a hand up from Priya. I'm sorry, Priya, I didn't mean to kind of preclude your question. Would you like to ask something?
Hi, no worries at all. Maybe this is a really basic question. I'm kind of new to the blue carbon mapping, coming from Delaware here. I'm curious to know how your current methodology allows for ongoing monitoring and not just single points in time for wetlands, since they are so variable. If you did cover this, I'm sorry. I might have missed it.
Thanks for the question, Priya, and yeah, happy to go on this. I'd recommend the write-up that's provided alongside this, which goes into all the data sets that are proposed here. But just to highlight one, we often have to answer the same question, and in this case, we rely on NOAA's Coastal Change Analysis Program, which explicitly takes repeat measurements and focuses on change in wetland extent over time. So that was a challenge in the 2018 National Working Lands Carbon Inventory, that wetland extent wasn't allowed to vary as flexibly as we propose here. And it's a really important fact to consider given the changing conditions of sea level as well as land use change. So that's how we propose capturing the extent within this method.
Thank you, Kyle. We have another follow-up question from Adina Payton, and then I'll get back to your second question, Priya, in a moment. And she asked, in addition to gas and soil compartments in these wetlands, there are also fluxes in the water column. Can these be incorporated?
Really great question. So currently we incorporate fluxes as they are measured by eddy covariance. Wetland systems are unique in their level of lateral transfer as well as water-based transfers and water-based fluxes that are not well parameterized currently. So we calculate terms insofar as the atmospheric change, but we can't currently capture fluxes such as lateral fluxes out of wetlands into subtidal regions.
Thank you, Kyle. Let's see, we have another question and comment in the question and comments feature from Jason Sauer. How will this model capture changes to carbon sequestration and storage resulting from coastal restoration activities that you listed among the state's nature-based solution goals?
Jason, thanks for the question. And it's a difficult problem, right? So currently there is not a comprehensive map of all of the restoration that has occurred in California's wetlands across all these types. There are resources that do a better job in certain regions. For example, re-wetted soils in that category are fairly well tracked through the Delta, and we do have a good understanding of where re-wetting and restoration has occurred in those systems. However, we have a fairly limited understanding of where coastal restoration may have occurred. And as far as inland wetland mineral soils, we have far fewer data. So in those systems, that's again where we start to rely on remotely sensed data. Our goal in those systems is in the absence of reported management data, we can still capture the effects of restoration as they change vegetation composition or tidal inundation, meaning they change elevation, kind of two of the primary ways in which we change wetlands for restoration. So hopefully that answers your question. I'll just add, sorry, Jim, not to interrupt you. I'll just add, I would highly recommend the upcoming workshop or listening session on management that will happen. I believe it's on, is it February 21st, Jim?
Yeah, February 21st from 10 a.m. till noon. And on that note, I'd like to go to another question in the comment section from Robert Short. In the literature I've read, because wetlands are flooded systems and generally anoxic, nitrous oxide emissions are usually very low or even slightly negative in both freshwater and coastal wetlands. Are there other reasons why nitrous oxide is an active area of inquiry for this inventory?
Thanks for the question, Robert. N2O, I think, is always an interesting topic, right? For folks, N2O has a very high global warming potential compared to something like carbon dioxide and methane. So it usually receives a little bit more attention because of that. It's also a source of attention here because we don't have a clear understanding. You know, we've read literature kind of going both ways on this, and we don't have a clear process-based model or a definitive answer on it. So that's why it's an active area of inquiry, because it could be a substantial portion of the budget, but we really don't know at this point, and we hope that we can continue to learn more as the science progresses.
Great, thank you, Kyle. At this point, we're still soliciting some more questions and comments. Priya, I know that you were asking a follow-up question. I don't see any other hands raised, so if you still wanted to step up and ask some additional questions or post some comments for Kyle, we'd be more than happy to entertain those. And we'd be more than happy to entertain any other questions or comments from anyone else in the audience. Priya, you're here. Let me just give you the ability to talk. Please state what your question or comment is for Kyle.
Hi, sorry, I didn't want to leave you hanging there. I think I'm still thinking through my question, but roughly I'm curious as to if maybe not now, but down the line, you'll be able to connect observed changes in salinity with the current data sets you're using and connect it to activities on adjacent land use types, say from the ag sector or things like that. And how might that connect to how might you connect wetland changes and emissions changes to activities and management outside of this type of land use or land type? I'm sorry.
Great question. So salinity being a pretty important driver here for methane emissions, we try to capture that as accurately as possible. Salinity in its particular case is a hard one because our current data we have for detecting salinity at the correct temporal scales is the NOAA buoy network and other water quality monitoring stations throughout the state. Those are inherently connected to the lands they're adjacent to, and they're not in every land. So at this point, we would not be able to connect for example, changes in salinity to particular management or other, adjacent land use categories for wetland quantification. We do strive to get the most accurate understanding of salinity that we can within these systems. But, again, with that limitation listed of the data available to us.
Here we have another question, Kyle, from Kathleen Ave. This question is not specific to wetlands. Sorry, this is related to another session. Early in the day, you indicated that the inventory data will be available at scales useful for local governments, air districts, etc. Can you include utility service territory boundaries in the same way they are available in CalAdapt? This would be very useful for utilities seeking to include nature-based solutions in our carbon reduction plans. Thanks.
Yeah, thanks, Kathleen. So yeah, for this inventory, we're trying to make it as useful as humanly possible, not just at the state scale, but at the county-like scale. So this could include other aggregated groupings that are similar to size. So this could include potentially air districts or special districts of other sorts. How exactly this data is distributed publicly, yet to be seen. So we'll be working on that when the time comes to actually distribute information and data. But we're glad to hear that that people are interested and might find this information useful. So thanks for the input.
Okay, at this point, I'd like to pose a last call for questions to comments for Kyle regarding the carbon inventory as it's modeled for wetland environments. Does anybody have any questions or comments they want to pose to the forum by raising their hand or put into the questions and comments section? Okay, not seeing or hearing any additional comments or questions for Kyle at this point, I want to remind everyone that this is not the only opportunity for any of the audience members to comment on all the different methods for calculating the carbon inventory for the different landscapes and pools presented. The nature-based strategy section has an associated programmatic website that they can go to find a public comment feedback feature where they can submit comments there. They're also invited to use the email address shown at the bottom of the screen right now. And so that's another way that you can follow up and provide feedback on any of the material you heard today or provide any comments or questions at that point. I'd also like to point out the fact that following this workshop, we will be posting the slides using this workshop up there. Those are already up there. But what we will be posting in the future is a recording for those of you who actually want to go back and listen and see the slides in real time that way. And finally, it's been mentioned a number of different occasions, but in a couple weeks on February 21st from 10 a.m. to noon, we'll be hosting a public listening session with regards to collecting land management activity data in terms of how well it's going to serve the state in tracking their ability to meet the targets regarding nature-based solutions. So that's been mentioned a number of times today, and we're going to focus on that particular area of interest at that time. Again, that's going to be on February 21st from 10 a.m. until noon. Thank you very much.